Mind your voice being yo yo. Okay, we are just about ready to go, I think. Sine wave, show your face in the chat, bro. Evening Lowry, always number one, bro. You're always number one, number two, straight up in there. Notification gang. Evening 13BTR. Yes, I was just actually dropping a message to a couple of people to let them know that I am live. Oh, freaking hell. I just opened this bottle of water. A sparkling water. Oh no, I can't believe it. What a disaster. I absolutely hate sparkling water. It's disgusting. Yes, I was just having a play on the new Xperia. It's beautiful. Really nice phone. Very, very good camera. So, sine wave. What's up, my man? Let's do this. Add as moderator. Can manage blocked words and change chat modes in live. Probably don't need that. Yeah, that's probably fine. I don't even know what my blocked words are, but what's up, sine wave? Oh man, why would anyone drink this? Sparkling water. Oh, mate, that is not the one. Although, that second, I don't know, I could get used to it. But that's not the one. Yeah, you notice the old crowns in the background there. Yeah, I do have a bit more real estate there. There we go. Yeah, I've got two of my Crown Macrotechs. I just literally recently brought them up from my old place this weekend. I still had a bunch of stuff at my parents' house. Brought up my two Macrotech amps, and I've got an iNova Pro MSA 1000. I've actually got two of those. One of them I blew up while breaking in a DD3518 a long time ago, years and years ago. And got the other one that's up here working as well. So yeah, we might be using those at some point. Maybe not. Maybe in this stream. Maybe not. We'll see. So how's your week been then, guys? Give me a shout. Let me know what you've been up to. Right, today is going to be some good fun. You guys who have joined the stream, actually let's just see how many people we've got. You're going to get a nice early look at a video that I am working on. Put some gin. Nah. What's up, Annibal? What's up, Quadfeed? Latvian video, hello. Just Count, what's up, buddy? Hawaiian, what's up, my man? Raw Cat, nice, nice. All the guys jumping in. Love to see it. Rockcat says, Sam, at the moment I have a Hertz HDP4 on the bench measuring distortion and stuff. Is that line any good from a build point of view? HDP4, I can't remember off the top of my head what that one looks like. HDP4, is that the IRS 21844 based mono? But from experience on the Hertz amplifiers, they have had a bit of bad experiences in the past with with preamplifier issues. So I would probably, if you've got distortion, turn your attention to the preamp and see what you got. Larry says, smell test first. Well, fortunately, Larry, the amplifier we're going to be looking at this evening doesn't have any problems, and I'm not going to be repairing an amplifier this evening. We're going to be looking at a new amplifier, one that's been released recently, and going through it, seeing if it's any good. And I'm going to be taking notes as I do so for an upcoming video. So you guys are going to be, you kind of got the VIP experience of being part of the kind of script notes taking for the video which is going to be released on this amplifier. Actually, what even is this stream called? I forgot to name this stream. What's it called? Live amplifier repair midweek. Oh, I mean that does still kind of count. It is still a midweek amplifier live repair. Yeah, let's just keep it as that. Thursday midweek. I'm working on a powder coating a racing sim chassis for Snoop Dogg. Really? I didn't see him as a sim racer. What's up, Tom? Just finished repairing my first Macintosh. Nice. Macintosh. Just picked up a Rockford T1500. Nice amps. Is there anything I should look out for with this amp? It gets hot real quick. It shouldn't get hot real quick. Although only under use. If it gets hot quickly while it's sitting there idling, that's something you should look into. But if it gets hot under use, it's kind of one of those things, isn't it? Like is it an early? I think it's an early-ish Class D. There's definitely lower RDS MOSFETs out now that weren't out when the amplifier was designed, so it's probably just using higher RDS FETs than more modern stuff. Right, guys. So, like I said, we are going to be looking at a relatively new amplifier that has recently come out, and we are going to be seeing whether it's any good and making notes on what's good and what's bad about it. So, I have a I kind of wish that didn't happen. Oh, I need to change this hotkey. But we're going to be looking at a document here, good and bad. I'm going to be making notes on the good and bad of this amplifier and seeing what's up with it. So the amplifier that we're going to be looking at this evening is the latest offering from Taramps, the Big Boss 8. I believe it's their latest offering. So there's nothing wrong with this, like I said. This amplifier doesn't have a fault that I'm aware of. It's pretty new, and we're going to be looking at this to see whether it's any good, going through its repairability, looking at the circuit design, see how it differs from the Smart 5 and all that jazz. So let's crack the top open and get started. See what we have. Let's get the screws up there. So obviously you guys are seeing this for the first time as I am. So you can get the old live reaction with the circuit and see what we find. I'm going to be going through it in some pretty big detail. So those of you who are really into amps and circuit designs and stuff, then this will be one for you guys. What's up, JNM? Thanks for jumping on the stream. So off the back comes. Donnell, have you have taken the back off this before, haven't you? All right. I'm going to flip it around this way because I'm more used to seeing the power supply on the right hand side. Okay. What do we have here then? What do we have here? Yeah, you have. Nice, nice. No burn holes. Yeah, no. Like I say, this is going to be an amplifier circuit design overview. Oh wow. Okay, I'm seeing some differences here already. This is quite a different design to the Smart 5. Wow. Okay. Okay. Different layout as well. Everything's in a very different position to how basically Taramps have been doing their amps for some time now. Okay. Nice. So let's walk you through and let's have a look at this thing together and see what we can find. So we're going to start off right at the power terminals. So we have the same type of power terminals that we saw on the Smart 5 and the Smart 5 Base, etc. We have the two grounds here, which are on the either side, nice and close to the common ground trace, which runs all up the side and on the underside of the PCB. So that's really cool to see. And then we have a dual terminal 12 volts, which has a nice big thick bar running all the way down the middle, which then branches off and supplies the 12 volts to the primary winds of the transformers here and here. So that's really cool. That is like extremely sturdy, stable, nice thick bar there for your 12 volts. And in addition to this bar, it also is backed up with traces as well. So this isn't the only thing that the 12 volts is going to be sitting on. It's actually also got traces for the 12 volts as well. So plenty of metal there, plenty of low resistance trace and bar for the 12 volts to come into the amplifier. Obviously we have our power supply filter capacitors, not really very important or super critical, so there's no point really looking too much at what they are. They're 25 volt, 4700 microfarads, and we've got a few of them there. There's definitely space for more, but they don't actually do much. All they do is just filter the noise generated by the SMP and prevent it from going back down the vehicle electrical system to making noise on other components and other parts of your vehicle system. So one thing I do notice is the fans are different to other tire amps that I have seen. These are much thinner little fans on the actual side plate itself. Okay. Now, interestingly, I actually think that these fans will be a hindrance, possibly, or at least not doing much. And the reason I say that is because the main fans are over here on this side, and notice how they are stepped away from the side plate a little bit. They're not directly up against the side plate, and that might initially look like, oh, that's just because obviously the terminals are in the way and there's not enough space, so they just mount the fans a little bit further back. But this mounting of the fan slightly further away from the case here is actually greatly beneficial and will increase airflow through the inside of the amplifier. Having a fan right up against the grate here is actually not very efficient. It's not a very efficient way of getting airflow through. Having the fan slightly set back from the end plate here allows the air around the fan and either side of the fan to accelerate after the fan, and basically creates more airflow. So having it stepped back a little bit is more beneficial than having it right up against the grate here, right up against the side plate. And obviously having these fans here doing pretty decent airflow out of the heatsink here is going to suck air in from this side naturally anyway. And I don't know whether having these thinner fans here, which aren't going to be able to chuck as much airflow through as these ones, is actually beneficial, or whether they might actually just get in the way, because you know the actual fan kind of blocks potential. There could have been much more open kind of grating here and stuff to let air in this side rather than having a fan in the way. So I don't really know if I can do any tests on that, but nonetheless. So like I say, 12 volts comes in here, sits on the primaries of these transformers, and then it sits on the power supply FET ready to be switched to ground very, very quickly, creating oscillation on the primary winds, which then gets converted into a higher voltage for the secondaries. Now let's take a quick look at the power supply FETs. Now this board looks even better than the Smart 5 in terms of like the PCB thickness, the cleanness of the assembly, the layout. It looks really, really nice, to be fair, guys. This is a pretty nice quality PCB. You can see we've got gate resistors are here, the smallest resistor, and they are 4.7 ohms, very, very low for a power supply MOSFET gate. So this power supply side is switching quite hard. It's not a soft switch power supply. I imagine that that wouldn't pass the EMI regulations for many countries. You'll notice if you do amplifier repair that some of the amplifiers that have come out of Korea in recent years, notably I think the Sundown Salt series and some of the Orion HCCA amplifiers, the newer ones, in the power supply side, they use 270 ohm gate resistors, which is monstrously high, and it really soft switches the MOSFETs in the power supply side, which does take away from their ability to pass full power. And the reason they've done that is to get the EMI under a certain threshold to pass these regulations for certain countries or certain regulations. But I imagine that Taramps are getting around that somehow, or don't really care too much about that, because they've never cared too much about it in the past, and their amplifiers certainly throw out a whole bunch of EMI, especially with the output section in their older amplifiers. So I don't think that's too much of a concern for Taramps, and the fact that we see 4.7 ohm gate resistors here on the power supply FETs kind of leans more into that as well. Let's have a look at what power supply FETs we're using. Now, Taramps are fantastic in the way that they don't actually mask off any of their components. They just leave everything out in the open, and they even often mark the PCB with what components are supposed to go there, unlike your Sound Digitals and stuff, which will do everything in their power to hide what parts are actually being used. So what do we have here? We have got all the thermal paste over my bloody hand now. I'm not sure you guys will be able to see that yet, but I'll bring up a data sheet. We can have a look and compare it to what's been used in the past. 180N 180, sorry guys, my head's massively in the way there. Just reading this part. 180N 4, oh, I can't read it. 180N, looks like 4FB, but it should be a number after that, surely. Let's bring up a data sheet and let's see if we can figure out what they are. Is it FDA? I'm just going to type in 180N for F6. No, that is correct. 180N, oh, STP, there we go. Let's have a look. RDS on is 2.7 milliohms, which is nice and low. The power dissipation, 190 watts, not as high as some others that I've seen, and so that means the die is probably on the smaller side. Typically, the larger the die, the higher the power dissipation, just because there's larger surface area there for the die to create and dissipate heat to the package and then therefore to the heatsink. Very low on resistance, I would agree. Very low gate charge. Let's have a look at the gate charge. 130, yeah, pretty low. Pretty low considering this category of FET, so yes. High avalanche ruggedness. Well, we can't see a value for that, but we'll just have to take their word for it. Low gate drive power loss. Switching applications, power tools. Okie dokie, so let's have a quick look at the specifications of this part. It is a 40 volt part, so this is on the low side of sort of voltage ratings for use in these SMPs, and sometimes it can be beneficial to use a slightly higher voltage part than you would otherwise think you need, because then the FET actually performs better in the voltage range that you are using it in. If we take a look at the safe operating area graph, thank you, straight up, we can see here that we have the voltage down at the bottom, and this is a 40 volt part. So here we have our 40 volt limit. Okay, let's check you can still see that. And this here is the current that this MOSFET can pass at the different voltage as it increases in voltage. And these three lines are the width of the pulse. So this is a single pulse current limit, and obviously the smaller the pulse, the more current it can pass because there's less time. For the power supply, the switching frequencies in these power supplies, we're getting nearer to like we're actually above 100 microseconds here. We're even quicker than that. So we can look at this top sort of one here just as a reference. Some of these data sheets actually give you a 10 microsecond as well line, but this one's just given us 100. So if we take a look at the 100 microsecond line and we look at what this will be switching sort of like 14-15 volts, maybe up to 20, just because of how it works out around about here. So we're looking at 10 to the 1, 10 to the 2, so that is 100. So about 110 amps by the looks of it at the 100 microseconds, which is pretty good, not bad. Oh, hang on, is 10 to the power 1 or 10? Nah, it's 1, isn't it? It's 10, sorry. 10, 100, 110, 120, 130, 140. So it's just under 140. What does this list the ID as? 120 is the ID. And the pulse drain current is 480. So this part isn't actually quite as sort of beefy as the, I don't think it's as beefy as the 3077, but it is quick and it probably makes sense for them. You don't necessarily need like the most amazing powerful FET in the power supply side. And the safe operating area graph, yeah, that's acceptable, that's fine. What you don't want to see is you don't want to see like a really tiny triangle over here with it coming right down. So I think that's probably ample current for switch mode application for this amplifier. Let's have a look at the gate capacitance. Beep, 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 beep. Input capacitance 7K, on the higher side actually, considering that this is what looks like it might be a smaller die package part given the power rating of this, and it's not the quickest thing in the world either. Let's compare this to one of my favourite FETs, IRFB 3077. I just love this FET for no real reason for it being amazing. It's just one of the very first MOSFETs I dealt with, because the amplifiers that I learned to repair on were Band of Viking range, like the Band of Viking 7K, and it used these FETs in the power supply. And the power supplies in those amplifiers were extremely rugged, never failed. The Band of Viking series only ever killed output FETs and never killed power supply FETs. So I always have a bit of nostalgia for these parts. So you can see here that the maximum power dissipation of the 3077 is like twice that of the STP part here. Or getting on almost twice. So that suggests to me that the die size in the 3077 is larger. Although, yeah, the pulse drain current at 850 is also, by the looks of it, twice as high. So yeah, the 3077 appears to be a much more kind of beefy, rugged part. If we look at the safe operational area graph, if it has one, usually it does. Have I scrolled past it? There you go, maximum safe operational area. So at sort of 14, 15, 20 volts, we've got actually very similar. Even though this part is much higher voltage, the 3077, when you're looking at like 15 volts here with the 100 microseconds pulse, you're looking at about 110 amps. So it's about the same. It's about the same. So yeah, perfectly fine parts to be using. I have seen these used in other amplifiers as well, so that's cool. So I'm going to go ahead and put in the good side. I'm just going to make a couple of little notes in here. So terminal block for power, very sufficient, and symmetrical etc. Fans away from side plate, better air through flow. Sensible FET choice for PS side, low RDS, good graph for freak used. Hard switched with 4R7 gates, which is good for performance, not so good for getting DAB radio reception, but that's fine. Okay, cool stuff. Let's have a little bit of live chat. If you were to make some hat cam swag, I would totally buy it. That's actually a good idea. Getting like some caps made that have like the little camera on the front of them. That would be like so funny. Quadfeed says not glued. Oh, we're going to look at that in a minute. I don't think that there's going to be any issue there. We'll power it up as well in a bit. This is going to be we're going to take our time, we're going to look through every part of this board and we're going to identify good parts, bad parts, and we're going to power it up. I'm even going to maybe do some modifications on it just to see like how easily repairable it is. Like if you had to get one of these in and you had to repair it, can you how do you power this thing up safely in like service mode without the high voltage rails and stuff like that? So we're going to take a look at that, provided that's alright with Donnell, of course, if we just do a little bit of soldering here and there. Is it single rail? Yes, it is a single rail, Lowry. All of the Tyrants amplifiers are single positive rail. That's a good point, actually. About the fans, I just noticed the fans are actually blowing this way, not this way. I made the wrong assumption there. So it's actually sucking air in from this side, which has plenty of open grates here. So that's going to be good. And it's going to accelerate air down the heatsink this way from either side of the fan, so that the air that's sitting here will get accelerated by the fans because they're away from the grate here, which is good. So you get plenty of airflow down here, and then maybe these fans are just in case there's any eddy currents that accumulate around this area. It's just to help that airflow come out of this side of the amplifier. So that's actually maybe pretty well thought out. You would naturally obviously get air coming out this side even without fans there, because there'll be a positive pressure inside here from these fans, but it might help just to bring out any air that's kind of stuck in eddy current areas. So yeah. I want to see you break down the new Kicker Warhorse amps when they come out. Oh man, that would be sick. I would be gassed to see that. Like, given the Kicker Warhorse was a completely bespoke design that was like game changing for its time, I really hope and pray that Kicker haven't just gone to a generic build house and just got some generic off the shelf circuit. Like, oh man, I would literally scream if it turns out to be like a Sound Digital clone, like a SFB 12K or something stupid like that. If Kicker just like went, yep, we'll have like 10K of them, please. Friggin' no, piss off. I hope that they actually design something bespoke again, like they did with the Warhorse originally. That would be awesome, and I would love to check it out. Are you planning to make a video of this? So basically, for anyone that's just joined, we are looking through the Big Boss 8 on stream, but you're just getting a kind of behind the scenes view of my workflow, because I'm going to be making a video on this. So I'm making notes now on all the good parts that I see of this amplifier and all the bad parts I think could be improved, ready for me to make a video, a script from, and then make a video. So you're kind of getting a little VIP experience here, just of my initial findings. Like, this is the first time I've seen this amplifier here on the bench, so I'm kind of going through it together with you guys, and giving you my thoughts as they come. So I think let's move on. Reckon you could modify my EP 4000 to put out 5 watt. 5 watt. Do you mean 5K? Man's got some Crown PA amps. Yeah, I have, man, back in the day. So let's move on. So power supply FETs, cool, look adequate, and we'll power it up and we'll test that they have equal current sharing as well in a bit. Gate resistor value, cool. We have a 10 ohm resistor on the drain of every single MOSFET. That seems to then also lead to a ceramic cap. So we've got a 10 ohm resistor on the drain of every MOSFET, which then goes into a cap, which then goes to source. That's just charging the rail caps. So that will be working as a high pass. So I guess this circuit here, this RC network, has been calibrated to a specific frequency, so that any sharp spikes and pulses, I wonder whether that actually is a janky workaround to I wonder whether the MCU in this amplifier is switching the power supply FETs right up to 50% duty cycle, which will cause some pretty big spikes on the drains of these FETs. Typically with the SMP, you don't go all the way up to 50% duty cycle. You sort of hover around the sort of, or some amplifiers, between the 45 and 48% duty mark. Just otherwise you get this mad ringing. So I'm wondering whether the workaround or whatever, they noticed some mad ringing. Instead of adjusting the duty cycle, they've put a RC on the drain to source, which will sort of suppress the spikes that you get on the drain from being switched at 50% duty cycle. Interesting. We shall investigate that when we apply power to the board. But there you go. There's one on every single FET, and hopefully these parts don't get damaged when the amplifier fails. I doubt they will, because they are blocked. They're DC block. This circuit here, this little RC, will only allow current to pass at ridiculously high frequencies, higher than this power supply is going to switch at anyway. So the only way that this RC would get damaged is if, I don't know, you end up with a gigahertz or something, like, from the FET, which isn't going to happen. So that's going to be fine. You're not going to have to change any of these 10 ohms and capacitors, I don't think. However, what they are is they are another point of failure. Look how many of these little ceramic caps there are. There's as many ceramic caps as there are FETs, and although these ceramic caps don't necessarily have a super high failure rate, depending on the quality of these caps, you might get one fail, and then you've got a 10 ohm resistor from drain to source, which probably would just blow open before the FET died. In which case you then have one of these FETs without this RC on it, which might get a bit more spiky on the drain, which probably won't cause the amplifier to fail, but it is just more points of failure. And I imagine that this is either just something suppressive just to prevent, like a preventative thing, might not even be necessary at all, or it's as a workaround for some other design issue to do with how these are being switched. Anyway, let's now turn our attention, we've looked at the FETs and the gates, let's turn our attention to the transformers themselves. The Taramps, historically, with their other older amplifiers, have used the kind of square block transformer style, which actually are less susceptible to vibration damage than this style of transformer, this style. So I've actually kind of been in favour of them, even though there's arguments as to whether they're a little bit less efficient, whether this style is actually more effective than the square one. I haven't really looked too much into it, but from a visual point, I do actually prefer the look of these ones anyway. But yeah, these ones do tend to be a bit more susceptible to vibration damage. However, although it doesn't look like there's really any glue on here, okay, and doesn't look like there's any silicon sealant around the transformers, one thing I will say is that these have a powerous feel to them, by which point I mean these feel like rock solid. Now usually with these style of transformers you get a little bit of movement, like in the winds or in the transformer itself. That feels like part of the main board. It doesn't feel like something protruding, like there's absolutely no movement on that whatsoever. It is rock solidly secured to the PCB. You can even tell by the sound that makes. It's like very, very high resonance. There is not a single wind on here that's loose either. I suspect actually that might have just been like doused in resin or something. Not a single loose wind on that one. Not a single loose wind on this one. Again, it's like absolutely rock solid on the board. So I don't think you're going to have, oops, that's taken my main camera out. I don't think you're going to have any problems with shorted transformer winds on these amplifiers, provided the build quality remains up to this level, because yeah, these aren't going anywhere. Absolutely rock solid. This is better than all the Koreans you see. Like, this is fantastic. Yeah, I don't think you're going to have any problems with the transformers here at all from a vibration damage standpoint. And they are insulated from the PCB by this thick layer. It looks like a kind of piece of blank board. It's a kind of PCB material by the looks of it, but it's very thick and it is very, very up and away from the board. So yeah, it's not going to short to the PCB. It's definitely not going to short any winds. That's pretty awesome. Love to see it. So that's cool. Right, so we've done power input, we've done looks at the power supply FETs, looks at the gate resistor, looked at all the other bits around the power supply. There is actually a 0 ohm resistor that I'm a little curious about over here. There's a little jumper from there to there. And what's that for? Now this can just be a way to get a signal or a trace across another trace without having to do a via or something on the board. Maybe there's a ground trace under here. So this little 0 ohm resistor might literally just be a way for the pick and place machine to just make a little jump over there. And is that part of the gate or something? What's that? Oh, that goes to the fan, I believe. Does that go to the fan? Oh no, goes to the gate. Okay, so that is literally just a trace jumper for the gates of one of the banks of power supply FETs. And there's another one over here, and that is for the other bank. And does that go for all of them? Oh, that's pretty cool. I think that goes for all of them. Now that, now I don't know whether that's intentional or not, but that is really useful. So whether this 0 ohm resistor is just to jump over a trace, and an easy way for the designers to jump over a trace without having to do a via, or whether that's an intentional way to make this amplifier easier to repair. But guys, having that 0 ohm resistor there means that you could potentially just knock that off its pad, these two on that side and these two on that side. There's one there and there's one over there, and that would prevent the power supply FETs from getting gate drive, obviously, which would prevent high voltage rail getting built when you apply 12 volts in remote. And that might be a really easy way to get the amplifier into sort of a service mode, where you can diagnose issues on the amplifier side and the Class D PWM side without actually having the scary high voltage rails present, which I assume are going to be pretty high. The rail caps in this amplifier are 200 volts, so we're going to be getting near that. This is an 8 kilowatt 2 ohm amplifier. Although this amplifier is rated between 0.5 and 2 ohm, it's an 8K 2 ohm amplifier with current limiting to allow you to run it down at 0.5 and 1 ohm. So yes, we're probably going to be looking at getting on for 200 volt rail, so it'd be nice to not have that present ready for you to accidentally touch or slip your probe on. So to have it not there at all is great, and I imagine we might be able to knock those little 0 ohm resistors off their pads to prevent the power supply section from switching the transformers. Now the only issue is if that's not intentional. Okay, this is really, really important to think about. If that's not the intent of these 0 ohm jumper resistors, then by knocking them off the pads, the power supply FETs might not actually have any pull down between the gate and source. Now, when the FETs are connected to the circuit normally with these resistors in place, the FETs are connected to the power supply drive IC over on the other side of the board, which will have its own built-in sort of pull down to prevent excess kind of voltage from just building up on the gate leg, which it will do naturally. If it's just floating, not connected to anything like an antenna, it will pick up charge from the air almost, or just from stuff around it, and it will build up eventually enough charge to turn the FET on, which you obviously don't want the FET just turning on continuously while it's got 12 volts sitting there and ground sitting there, because it's going to explode. So you can only really remove these 10 ohm resistors, sorry, not 10 ohm, these 0 ohm jumpers, if there is pull down resistors across the gate and source. Now, I don't think there is by the looks of it. I think it's using the driver, which obviously if you remove the 0 ohm jumper, is not going to be connected to. Now, we do have a what looks like 1 kilo ohm. Yeah, we have 1 kilo ohm at the moment between the gate and source. Now, can I find a 1 kilo ohm resistor somewhere around this area after the 0 ohm jumper? Gate resistor, gate resistor, gate resistor. I can't see a 1K anywhere after the jumper. So that's a problem. If the jumper is knocked off its pad, and you're intending to do that to prevent the power supply FETs from switching, then you're going to have a bad time, because the FETs are all going to switch on. Let's test that right now real quick. Let's just knock one of those 0 ohm resistors off its pad to see whether that can be viably used to get the amplifier into service mode, ready for you to repair it. But from the looks of things, I would say no. It does have a kilo ohm between gate and source, but I suspect that that's nearer the driver, which isn't going to obviously be any good if you knock a resistor off between the driver and the FET, because then it doesn't have it anymore. What's up, Matthew? How's it going, buddy? H1 Snubber for EMI. Yeah, that's what I expected it would be. I just wonder whether they noticed there was like hella way too much EMI and put that there. Although given the 4.7 ohm gates, I suspect that the hard switching is going to create some EMI anyway. An EP4000 isn't going to put out 5K unless you run it on 240 volts. Well, I did run one on 240 volts, and I can tell you it wasn't putting out any 5K. What do you have to say about the quality of the caps on these amplifiers? It's not really important. I mean, it's using EPCOS caps, which are fine. It's a Class D switch mode amplifier, so it's not like an old Class AB amplifier where the rail cap sort of tiny characteristics impact the tonality or the sound in any way, because this creates an audio waveform via switched MOSFETs, and these are literally just rail buffers to deal with dynamics and as buffer and storage for the rail voltage coming from the power supply to soak up transients and stuff. So really, as long as the capacitors have enough life in them to last the lifespan of this amplifier, and enough hours on them, it's going to be fine. EPCOS, yeah, should be fine. The smaller ones in the power supply are Kentuo, like a no-name brand, but they'll be absolutely fine. It's not super critical. It's not going to really affect the amplifier's reliability or sound in any way. I think the obsession with capacitors comes from back in the day, old school stuff in like the 70s, 80s and stuff. As long as the caps are able to do their rated hours and at the rated temperatures that you'll be subjecting the unit to, then it's fine. Okay, so let's just grab the hot air gun and a bit of flux, and like I said, we're going to knock off the 0 ohm resistor from the gate path, and I want to see whether we get any 1K. I doubt we will, because I think it's over at the driver side. I feel like the obsession with capacitors is just because they're they're an easy to understand and very visibly obvious thing for people that don't actually understand electronics to look at in a circuit and know what it is and know what it does. It's you know, it's something that someone that doesn't know about circuits or electronics can look at and say, you know, and kind of like argue it with themselves or with other people online as to whether one thing is better than another because of the capacitors, or they're, you know, they're usually the first thing that's going to be failing in something. You know, if someone's got a circuit that's got a problem, everyone online will just be like, replace the capacitors, like, even if that has absolutely nothing to do with the fault. I think they're just a very obvious part of the circuit that's easy for people to understand what they are and what they do. Thus the obsession with capacitors, because everything else in the circuit looks a bit like black magic to someone that doesn't understand electronics. So, like I said, now we have lifted that 0 ohm resistor from the gate path of this bank of FETs. What do we have? I suspect we don't have 1 kilo ohm anymore. Huh, we do. Where's the 1K resistor then? Oh, that's awesome. That's a really, really good thing. Oh, I can't see it. Must be, is it, maybe it's on the underside of the PCB, because I honestly can't see it. But that's awesome. This this resistor I've just knocked off is feeding this bank of FETs here. 1, 2, 3, 4. Oh, sorry, 1, 2, 3. Okay, so the banks are 3 FETs wide. So yeah, these 3 FETs are being fed by this this tracer that I've knocked the resistor off, and we actually do still have 1K between OR gate and source of each FET, which is fantastic news. And that means that we can literally, if you're repairing one of these and you just want to get the amplifier side powered up without the 200 volt rails, just knock off these 4 0 ohm resistors in line with the gates, and then all of a sudden your power supply is inoperative. Awesome. That's cool. There's probably a quicker way to do that. You know, there's probably a quicker way for you to do that rather than the intended way. I don't know, like I said, I don't know if that's intentional. I wonder if Taramps did that intentionally or whether that's just a nice coincidence, because it does jump over another trace on the board. It does look like it might be just used to jump over from one, you know, just jump over a trace without using a via. But either way, that is a pretty cool coincidence that you can just knock that off, disconnect the gates, and you still have pull downs. But I'll probably show you a quicker way to do that. Rather than having to desolder four resistors, you can probably just desolder 1 or 2 maybe maximum. Okay, cool, so that's really great. Love to see it. So we've done power supply FETs, we've done the transformer sort of assembly qualities, good. Everything over here seems fine. We've covered basically every part that we can see over in the power supply side. So now let's move on and let's find where the power supply drivers are. Now we're moving on to the other side of the board now, where things are starting to look a little bit different. Actually, I'm just going to add to my notes here, because I'm making notes on this. Good. 0 ohm jumper resistors in series with each bank gate trace. Awesome. Remove for LV service operation. Cool. X-formers, extremely tight to board, thick insulative slab, no loose strands. Yep, rip camera. I don't know why it keeps doing that. I think I actually think the USB port on the camera is bad, because like if I slap the desk really hard, it's probably going to cut out. If I slap the desk, no, it doesn't do it that time, but it's whenever I sort of move something on the desk, it seems to cut out. Okay, yeah, so let's locate the power supply drivers now. So if we trace back from the MOSFET gate, we've got a couple of 8-leg IC. It's just hiding behind the rail caps here. I'm probably going to show you, are they on this side as well? Got one there, one there. We've got a couple over this side. Let's just raise this up slightly so you can see under this side here with these caps. Zoom in a little bit there. So we've got a couple of 8-pin ICs hiding here. Now what are they doing? Are they the power supply MOSFET drivers? Let's probe a gate. Let's have a little look. Okay, we have, yep, continuity to this one here, closest to the rail cap. So that's an output, that is pin 7. So I suspect that all 3 of those will obviously have continuity. 1, 2, 3. And then this next one will probably have continuity to pin number 5. Yep, there we go. So there's our A and B output. So this is the power supply MOSFET driver. Now, is this one next to it the driver for the other bank further down the board? I probe the gate over here. Okay, doesn't seem to be. So let's confirm. Oh, we've only got 2 banks, obviously, haven't we? Because we've got 2 0 ohm resistors. So yeah, this is the MOSFET driver for all of the banks on this side. So we've got 2 banks of push, 2 banks of pull, all driven by this driver. That's cool, no worries. So what's these 2 little parts then doing? We might not be able to figure that out before we power the circuit up, but if I just have a look at see what it is, I need to get a little bit of thermal paste on there and just rub it over the top to show the marking a little easier. What are you? You are a 393. Is that a little comparator? LM393. So we've got a 393 there. That might be doing something with the power supply voltage regulation, because I suspect that the power supply is regulated here in way by that it holds a sort of maximum rail voltage from 12 volts all the way through to 14 volts. That might be something to do with that. We've got IC19, that could be something temperature related. It has a trace that does go off. Oh, okay, we've got IC19 connects to the MOSFET gate there. Sorry, the MOSFET drain before the RC network. And what are you doing? You might be over current protection for the power supply. That would be something new. I don't think Taramps have ever implemented over current protection on the power supply side alone before, which would be really great, which would mean the power supply wouldn't kill itself in an event of an output side short like you get a lot of the time. What are you? That is OVPD or OVRD? I think it's OVPD. I'm just going to Google that marking. OVPD. Let's see what we find. OVPD. Over voltage protection device. Oh, okay. Obviously, as if the acronym is printed on the front of the component. What the heck, guys? You know how difficult it is sometimes to identify a service mount part by the marking on the front? Like, it's usually something completely unrelated to what it is. It's just like a code, like 2 letters or 2 numbers or something ridiculous. If this actually is what that is, that will be a new one. It's a little SOT. What package is that? Is it SOT 20? I don't think it's 23. I think it's a bit bigger than 23. It's a 5-pin. 5-pin. I don't know. I don't know what package this is. OVPD, SMD, 5-pin. There we go. Lots of people have searched for this. Oh. What's going on? I'm going to tell Google that I want it to definitely search for OVPD. Is it SOT235? It looks smaller than SOT23 transistors. Sorry, it looks bigger. Sorry, it looks bigger. What's that? Nope, definitely not that. They have markings on the bottom as well. Not usually, from what I've seen. Usually the bottom's just clean. Okay, maybe OVPD. Maybe D is like a date code. So I'm going to search for OVP and see what comes up next. We might have to power the board up to actually see what it's doing, see whether it has any stuff on it. It's 5-pin. Is it SOT23? SOT23 5. Let's just see what we get. LED driver OVP. The problem is OVP is like standing for over voltage protection, which is annoying. Maybe it's just OV. Okay, we'll come back to that in a bit, I think. It'll be interesting to know what that part is, but we can, when we power the board up, we can see what it's doing and get some rough idea. So it's got connection to the MOSFET drain on this side. This side is ground, so we've got, okay, so it may be using the power supply MOSFET drain as like a VCC of some kind, which is weird because that's very, very high frequency. We've got ground on this side, on this pin. So 1, 2, 3, 4, 5. So pin 4 is ground, pin 5 is possibly either in or VCC. Pin 1 connects to some pads that aren't used over here. But what else does it connect to? Does it connect to VCC coming? No, it doesn't connect to any VCC coming from the... Got a couple of resistors over here that it connects to. We've got a resistor to ground, so pin 1 might be some kind of, might be setting some kind of mode or operational mode or characteristic of this thing, because we've got a resistor to ground on pin 1, and we've also got, is that it? Just a we've also got a resistor through a capacitor to ground. Okay, so pin 1 has resistor to ground and resistor, an RC to ground. Resistor to ground and RC to ground. So that's probably some kind of frequency or some kind of like calibration or something like that. Pin 2 is pin 2, it connects to anything? Pin 2 might be NC, might be not used. I don't see a trace from pin 2. So pin 2 might be nothing. Pin 3 does connect to something by the looks of it. It goes over to this resistor. Ah! Pin 3 connects to the gate output. Huh. Pin 3 is connected to the gate of this. So, interesting. I'd love to know what that's doing. I'll have to look that up a bit more. So it has drain on pin 5, ground pin 4, gate on pin 3, and an RC on pin 1. Curious. We shall find out later, possibly. So the power supply drivers are 2N85, hang on, 2NB54 something. It's very, very small, can't really see it, but it's basically just going to be a variant of the 4227. It's going to be pin compatible with the 4427, so you can use any 4427 derivative there and that'll be absolutely fine. Good driver, and I suspect this 10 ohm resistor is in line with VCC. So we've got a big capacitor here that's likely buffering VCC for this chip. Oops, if we go on the positive side, we should have VCC pin 1, 2, 3, 4, 5, 6. Yep. And ground on pin 3. So, you know how earlier I said you could very easily disable the power supply by just lifting those 0 ohm resistors in line with the gates? Well, that's 4 resistors you've got to desolder. A quicker way would actually just be to remove this 10 ohm resistor that supplies a VCC to the drive IC, because that would do the same thing. It would prevent, bloody hell, bloody camera. It would prevent your VCC getting to the driver IC, which would then prevent switching, you know, pulses getting to the power supply FET. So that's just 2 resistors you'd have to remove. One on this side, and then one on the other side for the other side of the board. There should be another one of those over here. Yep, there's another one of those. Exactly the same circuit over here. Power supply drivers. So the drivers are in the middle of the board, and by the looks of it, I was looking to see whether we had another one of those OVPD chips on the other side. We don't. We only have one of those little IC19, little SOT235 package parts on this side. I'm not seeing one over on this side. So whatever it is, it's just kind of like the power supply as a whole. And it's just taking reference from one of these drains here. Whatever it's doing, we can find out. But I'm sure it's got something to do with this LM393 here as well. There's some circuit there that's doing something interesting, which we can try and find out later, but it's not present on this side of the board. Okay, so we've gone through the driver. Looks good, using, you know, known good drivers. Oh, a 5 from Josh Holden. Holy crap, thank you very much, my friend. Appreciate you for that. You don't have to do that. I'll try and get around to all of your live chats in a bit. But he says I replaced a bulged cap. It's 10 by 13 mil size. The replacement I got was the correct values, but only 5 by 7. Will it be okay being 1/10 of the physical size? Yes, sir. It'll be absolutely fine. Especially if the device that you're repairing is a bit older. Capacitor technology and, you know, size has greatly improved, as has everything else. Oh my god, this camera is driving me nuts. Yes, the physical size of capacitors for their ratings has got drastically smaller as time has gone on. Same with everything else. So, provided it's the same ratings, yes, no problem at all. You can continue to use it. Is that dead for good now? I have to make a video on replacing the USB port on the camera. I did look at that. Straight up kicky in the nuts. Holy crap, guy has come through with the goods. Thank you very much for being able to spend some time on finding out what that is. It looks like it is a current measurement IC, which would make sense, and that's freaking awesome if that's the case. If they've done that and they've actually put current monitoring on the power supply side, that would be bloody fantastic. Let's see. Let's have a look at the data sheet here. I know the camera's down, I know. So, okay, power MOSFET or IGBT. Switching node in the VS. COM, yep. Gate on pin 3, wasn't it? Yep. Not connected pin 2. And CS, which is the VCS output. Ah, yeah. That's fucking awesome. Thank you very much, Straight Up, for doing the research on that while I was busy. Does it have a package marking bit in the... Sometimes it does. Does it say what the likely package marking? Here we go. Top marking. Are they just some suggested marking? So it might be the same part as this, but just like the same function, but just from a different manufacturer, perhaps. Because those aren't any of the markings that I have. Oh, hang on. Date code and lot code. Who was it that said that there could be markings on the bottom? I've never seen markings on the bottom before, but going by this datasheet, yeah, the top markings mean absolutely bugger all in terms of what the part is. And the part number is actually on the bottom, which would be D and the IR logo. Huh. Never knew that. That's wicked. Hardcore 360 said, I did. Thank you. Wow. Good job, Hardcore 360. You learned the hardcore way. See what I did there? Nice. Good stuff. That has been added to my bank of knowledge. Awesome. So I'll check the bottoms of parts if I ever need to look at what they are in the future as well. That is freaking awesome, and that would make sense that we have a 393 next to that part. So basically pin 1 will be the output of that part. So if this part, you know, I assume it's going to be outputting a signal based on the amount of current that it detects across the power supply FET here. And once it's above a certain threshold that's calibrated by the passive components around here, this 393 is probably then going to be outputting, you know, a true or false signal that the MCU further up on the board is going to pick up and cease the PWM to the power supply FETs if it detects overcurrent. Freaking awesome! I don't think I've seen that so far on any Taramis boards. Oh man, this freaking camera, bro. Please come back to me. Come back to me. Device default, here we go. Come on. Unplug. Plug them back in. Maybe I've got error 70 on the screen, maybe that's why. Oh no, we have nothing on the screen, it's just off. Great. Okay, battery in and out, power cycle. Do you want to use this battery? Yes. Okay. Ah, there we go, Windows has detected it. Come on, come back. Jesus, man. A designed failure if it's one man down to warranty. Nah, I don't see that happening, to be fair. Ah, here we go, here we go. We are back in business. There we go. Yeah, I do probably need to change my camera setup here to be something a bit more reliable. OVPs for over voltage protection. Well, in this case, that threw us up the wrong tree because it's in fact over current protection. I don't think the OVP has anything. That's just the date code and the lock code. So that kind of would throw you off a little bit, wouldn't it? Anyway, right, so that's really freaking awesome. Love that. We've got that figured out. So the power supply side has overcurrent protection. I am so happy to see that. Power supply overcurrent protection. I don't know how we could test that. I don't know how we could test that because I don't think I don't have a car battery in here or anything like that, and I wouldn't want to try it because it would stress the components a lot. We could create an artificial short circuit on the rail. So if I shorted the rail to ground on the output side, deliberately, connected a car battery and tried to power the amp up, we would see whether the overcurrent protection actually works. But I guess time will tell because obviously as people use these, things will happen, and if you get blown power supplies as a result of blown outputs, then we know that that circuit isn't really working so well. It's not really saving the power supply section. So there's one thing I just noticed over here I wanted to have a quick look at, is this has a identification thing here. So see this board, this PCB design is used by the Smart 8, the Smart 8 base and the Big Boss 8. So the Big Boss 8 obviously isn't much of a different board. Well, it's the exact same PCB as these other two. So that answers your question. Is the Big Boss 8 any different internally in terms of the amplifier stage than the Smart 8 or the Smart 8 base? Well, it uses the same PCB, so it's going to be the exact same circuit. Now there might be obviously some slight differences to the components used, but given that all the MOSFETs and everything have their markings kind of etched on with the on the silk screen, the FETs are going to be the same, the caps are going to be probably the same, so there's not going to be much difference between them really. So the big boss is probably just like the RGB stuff. So I suspect that all of the stuff that I'm saying about this amplifier here will reign true for the Smart 8 as well. Which is interesting because I've actually seen quite a lot of people with Smart 8s like going down, like quite a lot of Smart 8s going down. So yeah, it'd be interesting. Must be output side faults. I can't really remember. Like I haven't seen any in the UK yet. This is the first Smart 8 in the UK as far as I'm aware. So, or maybe it's not. Maybe someone else bought one. I don't know. But it's the first one I've seen. Pull the FET being measured and inject voltage while monitoring the output. Yes, yeah, so, well that would just confirm that the circuit works, but what it wouldn't do is it wouldn't confirm that the circuit is well calibrated and is quick enough to save the amplifier in the case of a real overcurrent event. So obviously we can inject some voltage and get that circuit to trip, that's fine. I'm sure that circuit works fine, otherwise it wouldn't be included here. But what we want to know is that will it actually save the power supply in a short circuit or an overcurrent event? Well, I don't know if it would or not. We'd have to test that, which would maybe destructive testing. Anyway, let's move on now. We've done the drive circuit. We've looked at everything over this side. Let's look at the stuff over by the output side. We're going to firstly look at the MCU, which is in a different position to the other smarts and all the HDs. We have the MCU up here now, which is still based on the PIC fam. Oh no, that's no. Ignore me, that's the TL4074C. It's over here, this one. So this is that is the MCU. I don't recognise the model. I don't know if it's part of the PIC family still or not. It's not PIC something, it's not PIC something. So yeah, that's the MCU. And what that's going to be doing is generating pulses for the power supply FETs. It's going to be listening to various different inputs for protection signals coming from the output section and the power supply section, obviously with that overcurrent module there. It's going to be listening to the rail voltage level and the 12 volts level coming from the power terminals. And it's also probably going to have an enable output signal that turns on the output drivers and runs the LEDs. And it probably also might run the fans based on the audio level or the heat level as well. So what I want to know is that directly connected to the power supply drive ICs? So I'm doing things based on like common failures. So basically if the power supply fails, then if the power supply drive IC fails, it can sometimes send 12 volts all the way back up to the MCU, which kills the oscillator outputs in the MCU, which is very annoying because it means you have to get a reprogrammed one from Taramps directly. So if we find our inputs, which is here, pins 2 and 4 are the inputs for the power supply drive IC. Now let's see if we have a direct continuity to the MCU. We do. We have dead continuity straight to the MCU. I don't think there's a resistor in line. If there is, it's going to be a 0 ohm. Not that 0 ohms exists, but you know what I mean. Nope, so it's literally just straight up direct trace to the MCU. So hopefully the power supply drive ICs don't fail very often, because if they do, then you're going to have like a 50-50 chance. Well, it might be a bit less than that. It might be like a 70-30 chance of the MCU getting damaged in a failure event where the power supply section fails, which sucks. So I would like to have seen some kind of resistor there that could blow open perhaps, or some kind of protection for the MCU in case 12 volts comes down from the drive IC to the MCU would be nice, but it doesn't appear to have anything like that. But that's the same as all the other Taramps amplifiers since the beginning of time, pretty much. So okay, fine, no worries. The fact that there's an MCU controlling it, I have mixed feelings about amplifiers using MCUs, because in one case it's cool because you can obviously program its functionality to be exactly as you want. It's very simple for the amp designer to just program a chip to do everything you want and then send it signals various places. And I suspect that it's probably very quick to respond to its protection inputs and stuff like that. However, from a repairability standpoint and also from a longevity, future-proofing standpoint, you know, let's say you still have this amplifier 30 years later, tariffs may not even be around anymore. You never know what can happen in 30 years. Or they may not, they certainly won't make this amplifier anymore, and they may not even have the ability to program new ones of these MCUs, and these MCUs may not even be available as blanks anymore either. So that could be a real problem in the future with repairing one of these if it needs a new MCU in the future, because you're going to have to like redesign your own PWM generation thing and like tie down all the enable and protection signals yourself with something like a 3525 or a TL494 or something like that. I know the camera has died again. So yeah, kind of good and bad points about the use of an MCU here. I would probably rather see a 3525. Just, it's simple, tried and tested, it works, it's quick to respond to its comparators. Yeah, there's no real reason to deviate from that tried and tested design, really, in my opinion, to something that needs programming by the manufacturer. Kind of annoying, but nonetheless, it's there and it does its job. Okay, let's turn our attention now to the output section. This is where we get interesting. So I'm going to pull off one of the clamps for the output FETs and let's see what we're using. It is actually marked there on the silk screen. STGW80H65. Is that what's actually used? GW, yes it is. Okay, let's bring up a data sheet for that FET and have a look. See what we're dealing with here. STGW80. I'm not typing. STGW80 H65. Let's have a look. So it is obviously a currently available part, which is nice. Oh, it's an IGBT! Oh, you love to see it. You love to see it. It's not a MOSFET. I am so happy that Teramps are back with IGBTs now. That is great. That is really freaking awesome. So basically, they didn't need to use an IGBT here. There are MOSFETs that, obviously the rail voltage here isn't going to be greater than 200 volts because the rail capacitors are 200 volts maximum. So there's plenty of MOSFETs that could have been used here, like IRFP 4227s. You've got the 300 volt ones, the IRFP 4868. You've got 4229s. There's like plenty of MOSFETs that would have fitted this circuit absolutely fine. However, those MOSFETs will have been running pretty close to their breakdown voltage, which means that the amount of current that they can pass at those voltage levels will be reduced, and they're just a little bit less reliable and a bit more sketchy right at their limits there. By using IGBTs, as you could see by the data sheet there, these things have a 650 volt limit, which is typical for IGBTs, much higher voltage. And IGBTs are very, very powerful in terms of their current capabilities as well. The drawbacks of IGBTs is typically that they are way slower than MOSFETs and they're more difficult to turn off. Often to turn off an IGBT, you actually need to drive the gate signal into the negative voltage range to really pull any voltage and any current away from the gate of the IGBT as fast as possible to get it to turn off nice and quick. So you do need different sort of drive design and topology really for really fast switching of IGBTs. So these things look pretty freaking monstrous. We've got trench gate field stops, so it's a It's a variation of the sort of classic IGBT. We have a internal diode from emitter to collector to deal with the huge high voltage spikes that you get from switching applications with IGBTs, which obviously would be required. If that diode wasn't there, you'd need an external diode on the legs or right on the traces by the IGBTs, as I learned with my inverter repair. What are the main features we've got here? Safe paralleling. That's good to see because we've got quite a few of these in parallel. Very soft start, very fast, soft recovery, anti-parallel diode. That's important for getting rid of these spikes, like I said. Very high voltage spikes. You can see spikes in excess of like 800 volts when switching IGBTs like this. High speed switching series. So let's have a look at some of the advertised specs. We have obviously 650 volts, which is pretty typical for an IGBT. We have continuous collector current of 120 amps. Now that is monstrous. That is very large. When you compare that to anything from like a 200 or 300 volt MOSFET, that is monstrous. Pulse collector current is not monstrously higher than, it's not wildly higher than the continuous. And that will probably just be a package limit, perhaps, or silicon limit, but that's fine. We're not going to be going anywhere near those values anyway. Power dissipation's nice and high, so we've got a big die in there, and obviously it's a large package component, so it's going to be able to get rid of some heat, which is what we want. Scroll down to the electrical characteristics. So let's have a look at ones that I'm most sort of familiar with. Whoa, you love to see it. Input capacitance. 10k picofarads. That is on the high side. I've definitely seen ones that are knocking on that, or as high if not higher. I think hang on a minute, the IRFP 4868 is not far off that, or similar. Might even be higher. It might even be 12k. So look, this is a part that Terrence could have used. Okay, this is a 70 amp MOSFET, 300 volts. So it's got to be a headroom. But yeah, much lower continuous. The power dissipation is actually higher. The pulse drain is actually higher, so the continuous we can kind of ignore because this is used in pulsed operation anyway. But the input capacitance of this part is also 10k, 10 grand, very high. Lots and lots of gate capacitance. You could use that gate, you could use that as a capacitor in lots of circuits for lots of useful things. That's crazy. But obviously the MOSFET here is fast. This is bloody fast for how powerful this FET is. 24 nanoseconds turn on delay, 16 nanoseconds rise, 62 nanoseconds turn off delay, and the full time is 45. Let's compare that to the IGBT here. Actually as well, the gate charge is kind of up high there as well. What's the gate charge of this one? Yeah, it's like twice the gate charge of the MOSFET. But yeah, look at these. So we've got, actually, you know what? It's not too bad. Turn on delay 54 nanoseconds. Current rise time is 33 nanoseconds. Turn on current slow, that's fine. Turn off delay time, so it is slow to turn off. The turn off delay is high. But I have actually seen slower FETs, slower MOSFETs used. For example, what's one that I can think of? Here we go. FDA 69N25. I think this might be a really slow part. So this is a 250 volt FET that again could be used in this amplifier possibly. We've got a 69 amp continuous drain. Pulse drain is similar to the IGBT. Power dissipation is about the same as the IGBT again. 69 amp, nice. Yeah, I'm sure they did that on purpose. Okay, so input capacitance of this FET is like a third of the 4868. However, look at the freaking delay times on this bad boy. This is slow. Turn on delay time, a typical of 95 nanoseconds, but acceptable up to 200. We've got a turn on rise time of 855 nanoseconds compared to the IGBTs, which are typically slow. See that? Wildly different. The maximum turn on rise time, 1720 nanoseconds. That is not a fast MOSFET. So IGBT, but this FET is kind of old. Like, when was this FET even released? I don't know. Do these data sheets? Here we go. May 2006. Right. So from 2006, this was the speed of a kind of high current, high voltage MOSFET. What's the date on the IGBT? When was this produced? Is there a date on this? Blah, blah, blah. Maybe it's at the bottom. Well, we've got 2013 there, but that might just be, that might not be the date of this part. But either way, this is definitely going to be a much newer part. Revision. Ah, here we go. No, it is 2013. So in, what's that? 6, 7, 8, 9. So in 7 years, we came from this MOSFET to this IGBT. When was the 4868? Does that have a date on it? Because obviously that's much faster. This is a very fast. This is 2015. So this is almost 9 years later. How much better high voltage, high current MOSFET technology became in terms of its speed there. Anyway, we're deviating a little bit. This is the IGBT used in the Taramps. I'm so happy that they're using IGBTs. Like I say, the Taramps HD line. Like, you remember the really old Taramps HD 10000? Lots of people ran this HD 10000. That thing was known for not being the most reliable amp in the world. But the thing that was unreliable about it was actually the power supply section. It was underbuilt. The power supply side of the HD10K was not able to keep up with what the output section can do. That was a 10,000 watt amplifier, and it used basically the same kind of output section in terms of, you know, IGBTs that we've got here. It used 8 IGBTs in the output section. I think they were actually only 300 volt IGBTs at that time, but IGBTs the same. And out of the, I don't know, tens and tens of those amplifiers that I repaired, most of them had never had any damage to the output section. It was always the power supply that failed in those older amplifiers. So the IGBTs are definitely a good choice for this this circuit here, and should make for a reliable output section. The driver is getting worked. We'll see. Yeah, well, the driver is different. We'll move on to the driver in a bit because it's interesting to see what that is exactly. So let's scroll down and have a look at this a little bit more. We've got diode switching characteristics. That's fine. So yeah, like I say, pretty quick considering its voltage and current ratings. And we have two different test modes here. So we have one at room temperature, you know, it's sort of 25 degrees I imagine, and then one where the junction temperature is at 175 degrees Celsius. So you can see how the values change there. So does it get turn off delay time? It gets much slower. So the hotter this IGBT gets, the slower it gets. Although the turn on delay time is actually quicker, but it's slower to turn off, I think. Is that right? Yeah. It's a fair bit slower to turn off once it gets cooking. And the switching losses also greatly get higher. They double when it's really, really hot. Let's see, does this have a safe area? Here safe operational area. Forward biasing, here we go. Safe operating area. So this amplifier is going to be knocking around the 200 volt rail mark. So we're looking at this line here. And if we go up to 10 nanoseconds, sorry, 10 microseconds we've got there, we're up at like 100 amps. That is fucking awesome. So yeah, like each of these IGBTs, when switched with 10 microseconds, is going to be able to pass 100 amps. Absolutely monstrous. When you compare that to the 4868, for example, this is only a 300 volt FET. So if they were using this instead, which lots of Korean amplifiers are actually using, blah 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 blah. Here we go. So again with the same rails, 200 volt rails, with 10 microseconds. Do we have a 10 microsecond? We don't. We only have a 100 microsecond. So it might be similar. Let's actually compare the 100 microsecond. So with 100 microsecond at 200 volts on the IGBT, we are looking at 10, 20 amps there maybe. So it can pass 20 amps with a 100 microsecond pulse. What about this one? 200 volts. Oh, it's actually higher. 20, 30, 40. Oh, the MOSFET's actually higher in this case. Interesting. That's not the result I was kind of going for there. Interesting. So this IGBT really does trail off as the voltage rises. Interesting. What is it? What about the 69N25? What about that one? Can you imagine a tech from 50 years ago looking at the datasheet for one of these parts? Yeah, I know, right? Bloody hell. Like, you go back 50 years and you can show a whole bunch of stuff and it's like, what? So this is a 250 volt part. So we're looking at 200, here we go, here's the 200 volts. So with the 69N25, we're looking at the 100, and actually, yeah, that's not even too bad. That's actually a little bit more. So, okay, interesting. So the IGBT isn't looking as good when we look at the safe operating area graph when it comes to, but I mean, the class D switching frequency is going to be faster than 10 microseconds here. So we're probably more likely to be, sorry, 100 microseconds, we're probably likely to be more up here. I suspect these other ones, these other graphs, like this graph doesn't have a 10 microsecond like curve. So although it should, if you're looking at it, it should be like up here above the 100 amp mark, we don't know if that's actually true because there could be a limitation in the package or in the silicon that actually would prevent it from being able to do like this IGBT with a 10 microsecond pulse can do like 100 amps, whereas this MOSFET doesn't give a rating for a 10 microsecond. This MOSFET does though, and this one is above the 100 amp mark. And this is actually a brilliant FET. Look at this FET. This kind of curve of the safe operating area graph is actually really shallow. The 69N25 looks like a pretty monstrous part, provided you can like switch it quick enough, because it's very slow. But okay, interesting. I might have gone for slightly different IGBTs in this amplifier then. Like on paper it looks like it would be pretty good, but the pulse drain current is like a little on the lower side. Power dissipation is okay, but not the most amazing. You know what? I'm going to just bring up on the PC right now, once I get my camera working again. I'm going to bring up some IGBT, because I've been doing some research on IGBTs and what ones I would fit to the inverters and amplifiers that I've been looking at. I'm just going to go ahead and look at what the specs are of a good IGBT I found. Yeah, my camera, it just turns off, like the power disappears. Really strange. I wonder if that's the power supply giving out or the camera giving out. Or maybe it's overheating. It could be overheating. Who knows? There we go. So it just needs a power cycle. Yeah, the multimeter cam's always buggy, but I have to fiddle with it to get it to work. So what we're doing, yes, I'm just going to quickly bring up my emails real quick, and I want to just look at a IGBT that I found from Farnell that was in stock, and it's a current part that I thought looked pretty monstrous. And we're going to compare the data sheets to the one that I found that I would probably maybe use. Here we go. So just from a bit of quick looking around, I like the look of this part. So 50 amp is that a little bit lower in terms of constant? Yeah, it's a little bit lower, but let's have a look at the safe operational area graph just to see whether this was one that I found for amps or whether, because this is quite cheap as well. This IGBT I found was quite cheap comparative to the rest of them. Oh, this datasheet doesn't have safe operational area graph by the looks of it. Okay, never mind. What are the other specs though? We've got pulse drain, maximum power dissipation, 714. So that's like twice that of the part that's used in the teraamps here. Pulse drain current is not very high, 150 amps. Okay, so that's not so great really. That's like half that of the other one. But it gets rid of heat quite nicely. Oh, actually, no, hang on a minute. This one's pretty decent. The collector current is at 100 degrees. The collector current at 25 degrees is 100 amps. So that's pretty monstrous. But the pulse current is only a tiny little bit above the constant current. Oh my god, that must have a massive die. Wow. That's pretty crazy. This yeah, like the data sheet of this one it's given, like it's the name of it and everything is given based on its 100 degrees Celsius rating, which usually isn't the case. That's crazy. That is crazy. Not too slow either. Input capacitance is 5k, not too bad. So yeah, this is a pretty good part. I wouldn't hesitate to use this IGBT in place of any of the ones in the teraamps amplifiers. Anyway, we have sidetracked a little bit. Those are the IGBTs used in the output section. Cool, love to see it. We have IC18 here, which is a little SOT235 part, very similar to what we saw in the power supply side. And I wonder whether that is the same kind of jazz as what we had in the power supply side by means of overcurrent protection. So we have pin 5 connected to the drain of what appears to be the low side FET here. That there should be connected to ground, so that should be connected to the source. Yes, it is. Pin 3 should be connected to gate, which is, yes, this is basically just another overcurrent protection. So we've got overcurrent protection on the output side by the IGBTs and on the power supply side by the FETs. That's freaking awesome. So IGBTs, we have a gate resistor of, what's that, 10 ohms. And we also have a parallel, is that a parallel 4148? Yeah, we've got a parallel diode and a gate resistor. So that's going to pull that down nice and quick. Love to see it. We also have a diode here from, is that gate to source. That's going to be a Zener diode, probably a 15 volt or an 18 volt Zener, just to clamp the gate drive voltage to prevent it from going above or spiking or anything like that. So yeah, pretty typical stuff on the output IGBTs. Zener diode between gate and source, diode across parallel with the gate resistor, and then this right here, if that's a 393, that's going to be, that is an LM393, yes, that's going to be part of the overcurrent protection on the output side. We've actually got one of those for each side of the amplifier, because it's a full bridge amplifier, so you've got two amplifiers on the same PCB here. So you've got another one of those circuits over here, which is great, love to see it. Okay, let's get to the big boy in the room, the output inductor. Now this is interesting because it's using a single inductor core, but with two wines on it, and I've seen this before in the teraamps HD 15K has this style of output inductor, and it's fine. It's perfectly acceptable to do this, no problems whatsoever. I don't know the benefits of it over two smaller ones, but with it being bigger, that does have a bit of movement on it, you know. It's not quite as sturdily seated as the power supply transformers were. You can see that it's got a bit of a wiggle. However, none of the wines are loose. and it doesn't wiggle by much. So although if this amp was mounted to a box, you might get a bit of movement there. Given how thick these leads are, I don't really see it snapping these anytime soon. I mean, maybe under huge heavy abuse it might. But this would benefit from a slightly less flexible like kind of silicone adhesive there, something a bit stiffer so that it didn't move. I mean, it is like siliconed down to the board very, very well, like it's not coming off anytime soon. But the movement is actually flexing the silicone. So if that silicone was less stretchy, then you wouldn't get that movement there. But I don't really think that's going to cause an issue. You've got something isolating between the inductor and the PCB, which is very important. In the first Smart 5s didn't have that, and they actually very commonly shorted the output inductor to the board, which caused the output section to fail. So the fact that that's there is good. That's a good sign. Okay, rail capacitors. Let's have a quick look at the rail capacitors. Obviously, we've got 5 rail caps. This is a single rail amplifier, single positive rail. We've got 200 volt, 2200 microfarads. So 2, 4, 6, 8, 10. We've got 1100 microfarads worth of rail capacitance, which is pretty monstrous. Love to see it. Okay, let's move on now to the drive circuit for the IGBTs. Now, these are drivers that we aren't used to seeing. So with the Smart 5 and lots of other amplifiers like the Powerus amplifiers, we have either the 20957S or we have the SI8244BB, which is a really good driver and has a really high voltage range. But this is something different. This is a UCC 20520. Let's bring up the data sheet of that and see what its parts are. Let's see what the so UCC. What was it? 20520. Okay, so this is a gate driver, which suggests that it can either be used for MOSFETs or IGBTs, the fact that it doesn't state. Wow. 5.7 kilovolt RMS, is that the voltage limit? That's insane. 4 amp, 6 amp, so pretty beefy by the looks of it. Single input, dual output. Okay, so the fact that it's single input means that it's going to be doing the, is it going to be doing the high and low side stuff internally? So it's going to be setting the dead time for high and low side and taking the high side supply and applying it to the signal internally. We'll have a look at the flow through chart in a minute. Oh, that's the isolation rating. Okay, no worries. Common mode, transient immunity, so there's immunity. Up to 25 volts VDD output drive supply. Nice. Wow, that's pretty high. I can't see you needing to go anywhere near that for these IGBTs. It's designed to drive MOSFETs and IGBTs specifically, so it's not just a MOSFET driver. Up to 5 megahertz. We won't be seeing frequencies anywhere near that on this amplifier for sure. The input side is isolated from the output by a 5.7 kilovolt reinforced isolation barrier. Nice. So let's have a look at the flow chart of this. So we've got VCCI into the sort of control, dead time circuitry, etc. PWM input, so the amplifier, that's PWM coming in from the conversion circuit, converting the sine wave into pulses. So we're going to have PWM from that circuit coming in directly, just as a single input rather than high and low side inputs like you would get with a 2010, for example. DIS, disable. Dead time control. I wonder what dead time can go up to. You're probably going to need some pretty high dead time with these IGBTs. And then you've got VDDA out, VSSA, VDDB. Oh, okay, cool. So each of the outputs can have its own supply. So we're going to have bootstrapping done externally. So probably the B side is going to be the one with the bootstrap supply with the diode and capacitor. Cool. Isolation. Nice. Okie dokie. And then we have functional isolation, which is literally just pins between them to prevent any arcing between outputs. Okay, nice. Excelente. So in this amplifier, what is doing the PWM conversion? Let's have a look. So what was the input pin? I think it was pin 2 or 3 or something, wasn't it? Blah, blah, blah. Oh, pin 1. Pin 1 is the PWM input. So PWM input coming in there. Now, where does that go to? I can't see the trace with my eyes. Okay, looks like we go here. This resistor, we've got a 10 ohm. Got a little 10 ohm resistor there. And where does that go off to? It goes through this little trace here, this little jumper there. Ah, here we go. Got something over there maybe? Yep, that resistor there. So this is an LM393 again. So the LM393 might be part of the circuit doing the conversion. We've got, what's this part? TL0, oh, so this is 072. Weirdly, this 072 looks like it's been laser etched and remarked. I don't know how well the camera will make this out, because it's not a very good camera this, but this 072 looks like it's got a matte finish. It looks like it might have been like etched and remarked, maybe not. It just doesn't really look normal, and it feels not normal. It feels kind of sandpapery. I wonder whether that is actually a 072 or whether that's not, that's something else, just to throw someone that's looking to reverse engineer this circuit off a little bit. Let's see if it has VCCs in the same place as other parts. So let's take an op amp that we know, for example the 074. Okay, yep, that's one of the supply voltages. And the other one should be over here. That should be, oh, hang on a minute, pin 1. So supply voltage should be on pin 4. Yep, and pin 8. Yep. Okay, yeah, so that probably is an op amp. Probably it might just be a weird package, a weird model that I haven't. Just a weird kind of texture on the top there. But either way, it's probably an op amp. It has VCC on 4 and 8, so yeah, it probably is. Okay, what else can we say about the output section here? We've got some linear voltage regs by the looks of it. We've got a 7805 5-volt reg. Is that going to be for... Okay, that's not for the op amps, obviously. We've got a 5-volt reg, and that's actually going into, possibly, the output driver on a couple of these pins. Is there any... There's another linear reg, or there's something going on up here. What's going on up here? We have this part here, MJD32C. Don't think I've seen one of those before. That could be either a transistor or it could be a voltage rig, but it's not marked as IC, it's marked as Q. So that's a transistor, but that might be being used as a voltage regulator of some kind, or it might actually be driving the fans. That might be driving the fans. We've got an optocoupler here by the looks of it. I wonder what that's doing. I wonder whether that's isolating maybe the signal side from the output side to prevent damage to the preamp circuit. Couple of... these look like drivers. I wonder whether these look like maybe boost converters. 2R2 and diodes here. Looks like might be a boost converter circuit. Alright, let's get some power into this amplifier now, and let's kind of see how it works, how it operates, what the operational modes are like, see how it kind of differs to the terms amplifiers we've seen before. Let's just read some live chat first. Don't forget the x-axis is RDS voltage, which when turned on is super low. I have a feeling you're thinking it's the full rail voltage, but it's RDS times IDS, so the actual VDS is lower. I'm not sure I'm following you. X-axis is the RDS voltage. What's RDS voltage? RDS resistance drain source, which when turned on is super low. I have a feeling you're thinking it's the full rail voltage. Well, yeah, I'm looking at the safe operational area graph and looking at the voltage and assuming that that's the voltage across drain and source. So for example here, VCE, voltage collector emitter, in this case of the IGBT, and IC. And this one, drain source voltage and drain current. So I'm just looking at that thinking, right, well if you've got, I don't know, 200 volts across the drain and source, you know, that's the voltage that's across them, then this is the current it can pass out of that voltage. That's what I'm going by on that. It doesn't say anywhere that it's showing the RDS voltage. It's just saying DS voltage, drain source voltage, which would be the rail. Anyway, let's take a look and get this amplifier powered up then on the bench and see what kind of frequencies we've got going on in here for the output section and the power supply section, etc. So we have the remote terminal on the output side again, which seems to be pretty common now on these amps. Okay, scope on, power supply on as well. Yeah, start off with the 9.3. Okay, so what should we look at first then? Let's look at the startup operation. Let's look at how the amplifier starts up. So the first thing I'm going to do is I'm going to probe the power supply MOSFET drain and see. Actually, I'm going to probe the power supply MOSFET gate. Let's see what kind of pulses we get on the gate. And it's going to be noisy because I'm using a times 100 probe at the moment for some reason. Okay, so we've got 5, the noise rejection. So we get tiny little pulses there, but those little pulses actually do draw some current. So it's not like other Taramps amplifiers that you've seen where you can kind of power these up with very, very, very low current initially. Those tiny initial pulses actually draw a fair bit of current. So it's a slightly different health check mode to what we're used to seeing. Ooh, that's some big spikes. That is some big spikes on the power supply drain there. That's up to 40 volts spikes on the power supply FET drain. Wow. And we're only in health check mode. Well, no wonder they tried to put a snubber there. We haven't even got to full duty cycle yet. Okay, interesting. Let's continue. So we should be building a little bit of rail voltage now. So if I go over here to the output side, let's see where our rail voltage is building. We have 82 volts there at the moment, and that slowly climbs, as you can see. Now the current draw has actually gone down a bit. And interestingly, so have the spikes. See, now that the rail voltage has actually built a fair bit more, those spikes are no longer present anymore. Interesting. I wonder if that's just a side effect of starting the amplifier up really slowly on low current. They might not be present in a vehicle with high current supply. Okay, so let's get this thing powered up to the full. So power supply switching frequency is 20 kilohertz on the nose, pretty much. So right at the limit of audio. Now that's pretty slow. That's pretty slow. Now why would you? Now the only reason you'd use a slower switching frequency like that versus a higher one is if your FETs weren't fast enough. Really, like I can't really see why you'd use a switching frequency that was like. Well, I'm not an amplifier designer. I don't switch my power supplies. I have no idea. But as far as I'm aware, the faster you can switch your transformers, the smaller they need to be for a given power throughput. And obviously the faster you switch your transformers, the more power throughput you can get through them for a given size. So by having 20 kilohertz is on the lowest side that I've ever really seen. Typically, car amplifier SMPs will be between 25 and 40 kilohertz. 20 is definitely one of the lowest that we've seen. I wonder why that choice was made. If they'd gone for like 40 or 50 kilohertz, then the transformers would be a lot more effective. So yeah, I'm sure there must be a reason for it that I don't understand because I don't design SMPs, but just going by that, I would have probably imagined it would be a bit faster nowadays given how fast FETs are. But yes, we have the health check mode, and let's have a look at the gate waveform as well as it comes in. Yeah, there we go. So, oh wow, the gate waveform looks pretty bloody fantastic, which you'd expect when you've got 4.7 ohm gate resistors on the power supply side. So yeah, super nice and fast, very, very immediate, on and off of the FET, looking great. Let's have a look at the drain waveform. When we go to full duty cycle, we do get a bit of a spike there, but it's not very high. It's acceptable. The snubber network's probably doing its job. Let's see actually, what is the duty cycle of the gate drive? I will need to change my settings a little bit here. Clear measurements, and let's go for source 1. Volt RMS, and then frequency and duty cycle 49.5 by the looks of it. So not quite 50. Yeah, if we was at 50, that spike on the drain would be a lot bigger. But it's still kind of there. But it's fine. I've seen much worse than that. And you can see that that spike only really comes in heavily once the duty cycle reaches. You can see that it's looking good, and then it's right there as we approach 50%. Okay, nice. So let's have a look at the rail voltage now. So obviously we've got 9.3 volts going in. So we're going to put our multimeter probe on the rail, which is here. We are 137 volts worth of rail at the moment with 9.3 volts. So on this amplifier, the rail voltage is proportionate to the input voltage, but probably only up to a point where it starts to self-regulate. And just before we go any further, I am actually going to put a load across the speaker terminals. It's not a good idea to run Class D amplifiers idle or anything without a load across the speaker terminals, because a lot of the time the output section relies on there being a load there to sort of allow the filter network to operate correctly. If you don't have a load across the speaker terminals, then sometimes the inductor and the filter network can present itself slightly differently to the circuit, which causes huge current draw through the LC and kills your output FETs or IGBTs, which you don't want. So I'm just going to drop a load across the terminals here while we're having this thing powered up, just for safety. Okay, let's go again, and let's see where the voltage regulation starts kicking in, because I'm sure that this will be voltage regulated. The rails are kind of low at the moment, sitting down here at 137 volts. So let's keep going. Up at 10 volts we have 142 volt rails. Up at 11 volts we have 156. At 12 volts we have 173. 13 volts we have 190 volt rails. And at 14 volts, whoa! We got 200 volt rails with 200 volt rail caps. It's on the limit of the rail caps, which is unusual to see. I mean, I'm sure there'll be a bit of headroom in them. You know, there'll be a bit of tolerance in them, but still, that's using, you know, they bought all the caps, they want to use all the caps. Okay, bloody hell. I was expecting some regulation to kick in there before we got to like 190, but no. Let's keep going actually. I hope it doesn't go above 200. Okay, no, even up at 15 volts, so it regulates like at 199, 198 on the nose. Like, yeah, it's literally just on the freaking limit. So if we probe the power supply MOSFET drain here, you shall see that as I get up to, actually you can see that the circuit is kind of optimized for, it's optimized for 14 volts. Look, as I go down, look at how that spike is like growing down at the 9 volts. So that kind of snubber network and this kind of power supply drive is optimized for 14 volts by the looks of it. And if we go above 14, you can see, oh yes, there we go. There's your regulation kicking in. Super low duty cycle, preventing the rails from exceeding 200 volts. So they are pushing that to the freaking limit. They are. Let's just hope and pray that that circuit remains operational, because otherwise you get some vented rail caps. They really trust those caps. Yeah, I'll fucking put some air protection on. That's a good shout. But although 200 volts sounds scary, okay, this is actually not scary at all from a repair technician's point of view. So although we've got 200 volts in those caps, this is the equivalent of having a half bridge amplifier on your bench with bipolar plus minus 100 volt rails, which is like you get 100 volt rails in like a 2.5K or 3K amplifier. So working on this amplifier here, Big Boss 8, the kinds of voltages you're dealing with internally are similar to that of a sort of 3K Korean half bridge or something like that with plus minus 100 volt rails. It looks scary because you're looking at a big number, but it's the same potential difference as plus minus 100 volt rails. So it's actually kind of low voltage compared to all the stuff I'm used to working on. The big half bridge 12Ks, you've got a rail potential of close to 480 volts. So that's where it gets scary. This isn't too bad. So it starts regulating at about 14.2. Anyway, we are obviously we're well within the limits of the IGBTs here. Now let's see, what is the switching frequency of the IGBTs on the output section? Let's power back up again. We're going to go back down to like 9 volts just to keep the rail voltage lower, just for, you know, just for nice stuff. Oh, one great thing which I love to see here is that when the amplifier is off, but there is still rail voltage present, like we've still got rail in here, we've still got, what's that, like 135 volts rail, there is absolutely no DC voltage on the speaker terminals. Great to see, love to see it, because in a lot of Brazilian full bridge amplifiers, you still get half rail on the terminals even when the amplifier's powered down, and if you short that to the case, then that can be bye-bye amplifier. So yes, with the amplifier off, absolutely no DC on the speaker terminals, love to see it. When you apply the remote, we get 12 volts there or thereabouts on the speaker terminals, which is probably just going to be some VCC leaking through from the drivers or something like that. Absolutely fine. And we only get half rail on the terminals when Class D switching initializes, which is right about now. And we get, oh, it's not the cleanest of outputs, but your sub won't see that. We get about, what's that, sort of 88 volts, which is, yeah, it's about half rail. And if we increase the voltage here up to 200 volt rail, you can see there we go, we've got 100 volts. So we've got exactly half rail on the speaker terminals, which is great to see. That means that clipping should be even, provided obviously it doesn't sag the rails too much under heavy load. Now you notice that it's a little bit noisy on there. So there is a triangle wave. Oh, okay, so I just found the low voltage protection cutoff. Where's that? So 9.3, 9.2, 9. Okay, 9.1 is the low voltage cutoff. That's cool. Just for your info there. So we've got, yeah, noisy triangle waveform on there on the output side, and that's just going to be a relatively basic filter network. So that's going to be sacrificing some noise reduction in favor of power throughput, which is not a problem. And I'll tell you why it's not a problem, because you connect your sub across the speaker terminals, and because obviously the switching frequencies for both sides of the amplifier are in phase with one another, means that you're not actually going to see a potential across the sub. So you see how on the scope screen right now, I'll just zoom into 50, on the scope screen right now, these triangle waveforms are in phase with one another, which means that the sub across the speaker terminals sees no potential difference. How do I get that to bloody clean up? Clean up. There we go. See that? No potential difference at all across the speaker terminals. Both of these terminals have identical noisy waveform on them, which means that the sub isn't going to see anything. So that's absolutely fine. Even though on the scope it looks like it might be noisy on the speaker terminals, no, the sub's going to see dead silence. No potential difference because they're in phase with one another. So that's cool. Just something there for you to see. Okay. So, idle current draw then, with 12 volts worth of input, considering this is an 8 kilowatt amplifier, 4.9, 4.8 amps idle current, not bad at all. That's pretty low given the amount of power this amplifier has. I'm curious to see how much of that is power supply side switching losses and how much of it is output side. So when we power the amplifier up just now, let's have a look. We actually rise up to just before output class D switching initializer, we get 3.5 amps just on the power supply. So the power supply, just oscillating at full duty cycle, is sucking back 3.5 amps, which is actually kind of high for a power supply section. It would be a bit less if that duty cycle was a bit under the 49.5. So the 49.5% duty cycle is it's like very high duty cycle for switching power supply MOSFETs at this speed. You could go down to like 48, 47% duty cycle, and that would actually yield a fair bit lower idle current. And you can actually see the idle current increases dramatically as the duty cycle gets to its limits. You can see that if I probe the power supply gate here, see if I can get it to bloody lock onto that frequency. There we go. So this is the power supply gate waveform, and you can see, look at the idle current compared to the waveform. Nice and low, nice and low, nice and low, and then it jumps up to 3.5 as it approaches. Actually, you know what? It actually jumps up to 3.5 even before it gets to. No, 3. Yeah, it's not actually the duty cycle. I think it's something else. Must just be some losses in the transformers then, because we actually approach 3.4 amps before we get to high duty cycle. So I don't think the lower duty cycle would actually help in this case. No, it wouldn't. Interesting. Okay, so most of that idle current is actually in the power supply, which means that the difference then between the power supply idle current of 3.5 and the output section idle current of 4.8 is only about 2 and a bit amps. So the idle current of the amplifier section is actually very, very, very low. That's really cool. Now guys, we're currently probing the output section low side drain. Look at that frequency. 40 kilohertz. 40 kilohertz, guys. And that's because we're using, well, I wouldn't exactly call these slow IGBTs, but that is one of the slowest Class D switching frequencies I have ever seen. That is very, very, very slow. You would not want to be using this amplifier on full range. I wonder whether the regular Smart 8 has a higher switching frequency. I bet it doesn't. That is very, very low. Oh! Yo! SineWave 02 comes in with a solid suggestion. It's the LEDs. The LEDs are probably drawing a fair bit of current. I wonder if we can turn them off and see the idle current drop. Depending on how bright they are, of course. Let's find the button on the front of this that turns the LEDs off. Here we go. So let's power this up. Can we turn them off? Oh, it's brilliant. You know what? It's so bright. It looks freaking awesome. I don't think you can turn it off. No, you can't actually turn it off. Oh, wait. Yeah, there you go. You can. There we go. So the lights are now off. Hopefully it remembers that setting. Oh, it doesn't remember that setting. Okay, so 3.9 amps idle current draw, 4.2 with the lights on. If I turn the lights off, come on, off you go. I'm pressing and holding the button because that's what turned it off last time. Well, that doesn't seem to be doing that anymore. I have no idea what I'm doing. But either way, yeah, we drop a little bit of idle current with the lights off. So the lights do contribute a little bit to the idle current, but not super lots, but just a little bit. But yeah, 40 kilohertz Class D switch. So yeah, you don't want to ever be using this on full range. You wouldn't be using the Big Boss on full range anyway, because I think it's a bass amplifier. But that is very, very slow. But it looks clean. Look how clean that looks. Barely any sort of ripple at the start. Very, very minimal. No spikes at all on the start and on the pull down. Yeah, very, very, very clean. How does the gate waveform look? Let's have a look. So this is the gate waveform. So you can see where the IGBT gets turned on right here. So the gate driver is like, yo, turn on please, bro. And he's like, "Blur." And that is at about 7 volts that comes on. You can see that, or maybe just a bit above that, maybe like sort of 8 or 9 volts. This IGBT turns on there. And then we're on, and then the off is nice and quick. We actually, you can see there, we actually get pulled a little bit below 0 volts. Not super lots, but we get pulled a little bit under 0 volts there on the off side of the low side drive. Cool, good. That looks perfectly nice. It's very, very slow, but it looks nice. Excelente. Okay, so what are these big resistors here then? Is that like a snubber for the outputs for the switching? Probably is. Can I get to that side? Not sure. I don't want to go poking around too much. Right, so we're up and running. Let's have a look at what do I want to have a look at? Oh yeah, I want to have a look at, see what the circuits over this side are doing. So I was curious what this little transistor up here is doing. So we've got 9 volts coming in from the supply, and then we've got 9.1 and 9. If I go up on the, so that's basically mirroring the battery input voltage, basically. Is it regulating it at all? 12.5, 14.0, 13.0. It's regulating it a little bit. So this transistor is taking the battery voltage and it's sort of stepping it down a touch. I don't know whether that's, might be for the fans, that might be a supply for the fans, so that the fans don't backfeed noise into the vehicle supply. I can check continuity to the fan headers in a little bit. I wanted to see what this area was down here, whether this is a boost converter for the IGBT drivers. So we've got a couple of what looks like PWM generator ICs here, and some diodes here as well. I wanted to see whether we are switching stuff around here. There should be some inductors as well. If that is a boost converter, we should see some inductors somewhere. Not seeing them right now. We've got 19 volts on there. Steps down. Here we go. There's some pulses. 16 volts. 16 volts. So we are regulating to possibly 12 volts there. 10 volts on the output. It's moving with the input supply. So if it is a voltage regulator circuit, it's not a typical kind of boost converter with an inductor, because I'm not seeing any inductors on the board. What's the VCC to the drive ICs? Let's bring up the datasheet to the drive ICs and let's see. VCC is pin, VCCI is pin 3 and pin 8. I'll probably go on pin 8. And then VDD for the outputs, obviously the high side is bootstrapped but the low side isn't. So we're going to check pin 16 and pin 8 of these. So pin 16 and pin 8. So pin 8's over here. That's VDDI. Let's see what that is. Okay, 5.2 volts. So that's probably coming from this 5 volt regulator here, I imagine. Yeah, so we've got 5.2 volts there from this 5 volt reg, and that's going to be feeding VDDI for the output drivers. Now, for the actual VDD for the low side, we've got 14.4 volts there, and that doesn't move with the battery voltage. Let's let the output side start oscillating for a second. Oh, okay, that's the high side. Okay, that's the high side because that's got the waveform on it. So it must be using output A for the high side and output B, VSSB, as the low side, which is going to be pin 9 over here. Which is over this side. Okay, nothing on there. 0 volts. Oh, it's VSS. Oh, I need to do pin 11. So that was ground. I need to do pin 11. Here we go. Here's pin 11. Pin 11. 14.9. Okay. So that, what's that created by? I'm not seeing a boost converter anywhere. This kind of circuit here with the diodes is doing some kind of voltage regulation. Maybe it's on this side. Maybe it gives 18 volts on the output and then it steps it and then it sort of regulates it. Ah, hang on a minute, what have we got here? We've got some reg, here we go, voltage regs. So this is using old school linear voltage regs rather than boost converters. That's interesting. Okay. So we're not using boost converters, really, although you could call this a boost converter, but not a typical boost converter to directly run the IGBT drivers. We've got a boost converter of some kind here, where we've got PWM on this diode here, which is taking your sort of 12 volts to, and that's then turning it into 18 or 19 volts, which moves with the power supply voltage. That then gets fed into a voltage regulator here, which is then regulating to 15. So we've got a couple of 15 volt regulators here. Interesting. So these are the voltage regs for the IGBT drivers on the heatsink, linear voltage regs. Fair enough. It's gone backwards a little bit, that has. Cool, cool, cool. Okay. What else do we want to look at? Let's have a look at something a little bit more simple now. Let's have a look at the side of the amplifier where the controls are, and let's see whether they actually line up with what they're supposed to be doing by injecting some signal. Let's have a look at some live chat. Oh, Andreas sends a 23.99 euros. Dude, that is awesome. That's a lot of money to throw someone on the internet. Thank you very much. Greetings from the Netherlands again. Thank you so much for the donation, my man. Greetings to you too. Hope you're having a great evening. Thanks for jumping on. Let's just read some live chat reel here right now. Yeah, talking about the rail caps. Yeah. Bump it up. You struggle to get a better amp than this, Jamie, to be honest. This is a really good amplifier. Like, there's not much that I would choose over this these days, to be honest. So basically, slower output Class D switching probably means that it's much easier for the output IGBTs to turn on and off reliably, but it does mean that you need a larger inductor for filtering out the frequency. That's probably why it's noisy on the speaker terminals. You see there's that triangle waveform on the speaker terminals. 40 kilohertz is heckin' low. Obviously the lower the frequency you need to filter out, the larger the inductor has to be. And it probably also changes the amount of current that can pass through the inductor, although maybe not. But anyway, it does affect the size of the output inductor you need. The slower the switching frequency, the larger output inductor you need. Isn't it similar to the MD8K? No, the MD8000 actually is got some similarities, but there's quite a lot different in the design. Now I want to get HK08. What's that? Oh, the hooligan. Let's have a quick look at this. If I recall, this is... Oh yeah, this is like... I can't quite see the driver board. I think that's using an IR2184 on the driver card there. That's a pretty old circuit design. I would obviously have to see one to determine how optimized it is, but given that this is a Korean design and they are very bad at rushing new designs to market without fully optimizing things, I would be a bit skeptical of this. If it's anything like the M21Ks and the other the DS18 versions of those, they were terribly optimized, awful things. It's the same picture in it. I want to get a picture of the output driver. But I can tell you right now, this amplifier is going to have no power supply current monitoring. If it has output side monitoring, it will be just by a shunt resistor on one of the rails and not on both. This is a dual railed amplifier by the looks of it. And you'll have a shunt resistor on probably the negative rail is what it tends to be. So if you get a short on the positive side, bye-bye power supply side. Yeah, you'll have a higher switching frequency on this though. Linear voltage regs again, and that will be with an auxiliary tab. Yeah, this is a really old circuit design. Depending how well optimized it is, it might be fine, but honestly I would go with this Big Boss 8 over this any day. The Big Boss 8 will probably bench over 20k on the dyno dynamically. But that is one benefit though. If you were wanting to wire into the dirt like 0.37, you are going to be able to clamp more power with a classic amplifier like that HK08 because it's not regulated. So it will just do whatever power you are asking it to do based on the output resistance rather than like it kind of regulating to make sure you're not clamping any more than 8 kilowatts. This amplifier right here on the bench, the Smart 8, this is actually as beefy or if not more beefy internals than the HD10K. So this definitely is capable of doing way more than 8K. Obviously it will do dynamically before the smart circuit kicks in and reins back the signal level, but yeah, you could definitely, if you wanted to, get more than 8K out of this. Or they could disable that circuit and get more than 8K out of this. So yeah, this isn't a full range amplifier, but I know that the Smart 8 is, I think, being marketed as a full range amplifier, so the switching frequency better be faster than 40 kilohertz, because otherwise that's not full range. Anyway, yes, I wanted to have a look at the switches and knobs on the side here. So what do we have? Obviously gain we have marked as 4 volts to 0.2 volts, so we can check that, see how accurate that is. High pass we have 8 Hz to 30 Hz, so we do have a fixed high pass filter and it obviously it says 8 Hertz, but we can check that to see what frequency actually starts getting attenuated on the low end. We have low pass. It says on the side it starts at 60 Hertz, which is again a little high. I would rather that said 40, because remember, low pass isn't a straight cutoff, it's a slope. And a lot of these big high power woofers just suck at playing anything over like 45 Hertz, and so you want to start attenuating the output level somewhere around about sort of 40-45 Hertz really, to make the most of the power you can throw into the lows. And SineWave 02 will be able to testify to that. Bass boost, I hate that they still have this on here. Selectable frequency 35 to 55 and boost. I just wish that wasn't there. No need for it whatsoever. So let's plug some power in and check to see how accurate all of those things are, because that's going to be a pretty big pointer for user, you know, just usability and the correctness of how it's used. And just before we do that though, one thing I do want to do is see how warm do the IGBTs get running idle. How much switching losses is there? So we're just going to pull them away from the heatsink a little bit, grab the thermal imaging camera, see how hot they run at idle. I would be so surprised if there was barely any heat coming off these at idle, given that it's literally switching at like 40 kilohertz. So there should be barely any switching losses. I would be very cross if they got hot fast, because that would be like, there's no need for that. There's no need for them to get hot fast at those low switching frequencies. Jamie says it will be loud and then all of a sudden a drop where the limit kicks in. Yeah, absolutely. If you are on the limit, if you are using the limit of the of these Taramps amplifiers, if you're sitting on the 8K limit, then yes, you will hear the dynamics be weird, because it's like removing power as it's kind of detecting you're going over it. So yes, you're not going to ever be able to continuously clamp more than 8 kilowatts out of these amplifiers, because that's what they're intended. They're intended to limit you to 8K. So if you want more than 8K, then yes, you either buy a bigger amplifier or you risk running another amplifier at a lower impedance to force more power out of it, which you can do. But that doesn't mean that this is a bad amplifier, because it's doing what it says. You know, if you don't want to clamp more than 8K, then this isn't going to clamp more than 8K, and it's probably going to be more reliable than something that's supposed to do 8K, but you're wired in the dirt, rising and clamping 13K. It's not going to be anywhere near as reliable in the long run. So we're going to start off nice and low again. Okay, so let's crank that up to 12 volts. Let's see where the hot spots are on the amplifier. So obviously the output drivers will be running a little warm, as they normally would. That's fine, because they're doing work. We have the boost converter circuit there running a little warm. That's absolutely fine. Again, it's doing work. We have this transistor over here running a bit warm. That's absolutely fine. Now the IGBTs, now they are actually getting a little warm here. After less than a minute at 12 volts, let's go up to 14, fuck it, why not? We are actually seeing 34, 35 degrees Celsius. But you will always get some switching losses with IGBTs, just because of how sort of slow they are, and you know, then they're not like super rapid like MOSFETs. So we're at 40 degrees Celsius off the heatsink after like a minute of idle operation at 12 volts. So if you are repairing one of these, that's what you should be expecting. That's perfectly normal. Power supply FETs shouldn't be getting hot at all. No, barely anything. There's like a slight glow, 28 degrees, 30 degrees. The ambient around it is like 24, so a tiny little bit of warmth, but again, nothing to worry about. Power supply transformers, got about 30 degrees on them. Output inductor is staying nice and cool. Well, it looks like it is. Yeah, it's staying nice and cool. So yeah, that's what you can expect. We now have 46 degrees Celsius on the output IGBTs. So because they're IGBTs, yeah, they're running a little bit warm at idle, but that's just something you got to expect when running IGBTs. I think the Banda 10K, yeah, pretty good amplifier. Again, uses IGBTs on the output side, and with the Banda 10K, it's not regulated, so you can force like 20K out of it at 0.5 if you want, no worries. All run 2 bass 5Ks. Yeah, again, the bass series from Taramis is pretty good. I think that these smart amplifiers are perfect for somebody that doesn't want to try and extract more from the amplifier than it's been designed for, and I think the smart amplifiers are a great one to recommend to the majority of people because they're much more idiot proof. Like if you did wire a smart amplifier down way below like 0.25, it's not going to try and make power that it can't make and fail. So it's a more user-friendly, more idiot-proof amplifier that I think is a good one to recommend to the majority of people. Yes, if you're power limited in a power limited class, let's say you're in like a competition class that limits you to 10K or whatever, running a non-smart 10K amp at 0.3 or something is going to get you way better results than running a smart amp here, because you're going to be able to actually clamp more than 10K, which you wouldn't be able to with a smart amp. But I think they're a really good option for the general average bass head that needs this kind of power, because they're a bit more idiot proof. The Banda Viking 15K, which is now what's more available than the 10K. I don't know if they make the 10K anymore. The 15K is kind of their new big one. I'm not a big fan. The output section doesn't seem that reliable. The IGBTs that they use are 300 volt parts. I recently repaired one and used 650 volt IGBTs instead, so that will be interesting to see how reliable that is going forward. So yeah, let's run some signal then into this amp and see whether the crossover stuff on the side is actually true to what it says. We still only have one RCA input. I do wish Taramis would give you 2, but that's their choice to just give you the 1. So gain down nice and low. So first thing I want to test is, I want to test the low pass filter, because that's really, really important. That's the thing that's going to cause the amplifier to not sound great to people if they don't know what they're doing. So the low pass filter is currently set at 60. So I'm just going to change my oscilloscope probe over to one that's a little bit more sensitive. A times 10 rather than a times 100. There we go. And we're going to zoom out on the scope to a much better one for audio frequencies, reject high frequency. Okay, we're going to AC couple as well, because we're going to be reading this small sine wave. So let's set the frequency generator to 33 Hertz to start with, which should be basically out of all of the filters. Okay, so plenty noisy as we know because of the triangle wave coming through. But that's okay, we can just zoom in, 10 volts divide. Now I know that looks really noisy, but honestly it's not. The subwoofer is not going to see any of that because it is in phase with the other terminal. So the subwoofer is just going to see a beautiful, pure, clean sine wave. And we can actually prove that. If you want to see on the scope what the subwoofer is going to see, if I get my other probe, channel 2, so I'm going to connect up channel 2 probe now, okay? Actually, what I should probably do, before we go any further, I should probably put these IGBTs, clamp them back to the heatsink, because I'm obviously going to be drawing a bit of current because we have a load connected now. So I don't want them getting toasty. So let's just put these clamps back on real quick. And yes, I'm doing this carefully because there is still high voltage in the caps. Yeah, both output inductors on the same core. You can actually do that, it's not a problem at all with how this is being used in full bridge class D. The switching frequency that is being filtered is in phase with each other. So yeah, I've seen that done quite a few times in smaller amplifiers, and also on the HD 15K, or sorry, the base 15K does this with a single output inductor. Okay, so yeah, clamp those back on now. Let's power it back up. So if I take both my oscilloscope probes here and do some channel math on the scope, let's turn them off and do channel math 1 minus 2. We're going to now see what is across is it plus? It still looks a bit noisy actually. I was expecting that to clean up perfectly, but it's still a bit noisy. So that's basically what your sub's going to see. Yeah, it's a little bit noisy, but your subwoofer voice coil is a low pass filter in itself. So yeah, I mean it's better than just probing one. So yeah, a little bit of noise. This is not an issue. This is not an issue at all. It's just a noisy filter network on the amplifier, but like I say, your sub's not going to see it because the noise is in phase on both terminals, so your sub sees no potential difference, and also your subwoofer voice coil is a low pass filter that isn't going to even see 40 kilohertz. So that noise that you see on the scope is not going to be seen by the sub. I kind of covered this in my video going over EMF's video about how some cheap amps kill subs, and I was calling them out on bullshit. So that's not an issue at all. So what we are looking for though is we're looking for the operational mode of the low pass filter. So the filters are all set to 0 on the side right now. So we've got 60 Hertz down at the bottom there. So what I want to see is when does the sine wave start tapering off. So we've got 17 volts RMS at the moment. So we are currently sitting at there we go. We're currently sitting at 17.5 volts with 31 Hertz. So if I go from 30 Hertz up to 40 Hertz, okay, interestingly, we're actually down at 15 volts now. So with the low pass filter in its minimum setting, it actually starts attenuating the sine wave as low as 17. So we've got 18 volts there with 25 Hertz. And I can see it visibly attenuating. By the time you get to 33, we're down at 17.2. 38 Hertz, we're down at 16.3. And then it really starts attenuating hard. At 45 Hertz, we're down at 15.2. And then up at 55 Hertz, we're down at 12. And then by the time we've got to 60, we're at 11 volts. And then we still get signal coming through 7 volts. We're up at 90 Hertz now, 100 Hertz. So you still got some 100 Hertz coming through, but it's like 6 volts, so it's pretty small. So it only really completely disappears once you get to about 170 Hertz. And that's your filter slope. But yeah, it's really interesting how it comes in and starts attenuating as low as like 30 Hertz when you've got the low pass filter set to 60. That's cool. I actually like that. I would much rather that, because the sensitivity of your hearing to higher frequencies is a slope, with lower frequencies being less sensitive, so you do want more power going to the lows. Also, modern car subwoofers are much worse at playing higher frequencies, so I'd much rather see, you know, a pretty, like a shallow curve like this, starting low at like 30 Hertz. That's pretty cool. Okay, let's set this to 60 Hertz. So let's say you actually want 60 Hertz at full chat coming through the amplifier. What do you have to have the dial set to in order to give you that? So full chat was 18 volts. So I'm going to start opening up the dial now on the side. As you can see, we're going up in voltage now. So if you want full chat 60 Hertz, you're going to need to have the low pass filter turned all the way up to 200. Because even that's fully open now. We've got 19.5 volts. Even if I put the low pass filter down to half, which should be like somewhere around the, I don't know, 130 Hertz, you can see we're down at 15 volts. So it's a very, very shallow curve. Very, very shallow low roll-off on this. So yeah, with the low pass filter set to minimum position, this amplifier is going to love the lows, and it's going to be really, really potent on the low frequencies. Let's check the high pass filter now. So the high pass filter is set to 8 Hertz at the moment, which is its lowest position. So let's just have a look and see where that starts attenuating on the high pass. So you can see we've got 16 volts RMS with 22 Hertz. Let's start decreasing that and see where that starts going down. So 16 volts, we're still at 16, we're down at 17 Hertz now. Wow, so this amplifier is like a proper lows monster. It's like, it's flat with the low pass filter on its minimum position. From 30 Hertz, it's flat from 30 Hertz down to 17, 13 Hertz. It's still pretty flat. We've still got about 16 volts. Wow. It starts attenuating very shallowly at about, very shallow at about 10 Hertz. Whoa. And then even at like 7 Hertz, you've still got almost full signal. We've got 13.6 volts there. There's a bit of THD on the sine wave. I don't know if you can tell. The shape of it is maybe looks a little bit slopey, but actually no, it doesn't look too bad. Even right down at bloody 4 Hertz, you've still got 10 volts, which is still not quite half. 3 Hertz, you've still got like 6 volts. So yes, that is a very low, very shallow high pass filter. If you wanted to, let's say your box was tuned at 33 Hertz. Let's say you wanted to start attenuating frequencies from 28. So let's go up to 28. Where would you have to have that high pass filter set to? So here's 28, we've got 16 volts there going in now. So our high pass, let's turn it up and see where it starts attenuating. The high pass filter I've currently got set to half. It's barely touched it, it hasn't touched it at all. High pass filter is now on half and it hasn't even touched 28 Hertz. If I go all the way up to 30, you can see that with the high pass filter set to 30, we lose about 6 volts. So yeah. I would say the high pass filter dial is like the frequency that the high pass filter starts being affected from, and that's where these dials are very difficult for the average user to kind of like gauge what they mean. So with the low pass filter dial, the number on the dial isn't the frequency that the filter starts working at. It's a value somewhere in between the curve. So if we do a little cheeky bit of MS Paint for you right now, okay, so if we just draw a curve, okay, from here to here, okay, if this is your low pass filter roll off, okay, this is your low pass filter, the number on the dial, like 60 Hertz, is going to be something like around about here. Maybe even like here. Maybe even like here. It's like somewhere around here is the number on the dial. Whereas for the high pass filter, I'm doing this really badly, by the way. Whereas for the high pass filter, this is the wrong shape. Fucking right. For the high pass filter, the number on the dial is more like up here. Right, like here. I guess. That might be wrong, but what I'm trying to say is the high pass filter number is the number that it starts affecting at, whereas the low pass filter number is the number that is somewhere in between the curve, in the middle of the curve. So that's kind of crazy. So yeah, this amplifier is going to be a low frequency monster because it's favouring the lower stuff. Cool. Right, let's check the gain. Let's just see. So the gain is currently at minimum, which is 4 volts. So if I set, now I'm probably going to have to remove my load. I don't really want to do this. I'm going to have to remove my load from the amplifier to do this. Maybe I won't do that. No, okay, so the gain's the gain, whatever. Just numbers don't mean anything really. Just set the gain to your clip point. So cool. We've done that. Okay, so we've gone over the dials and the filters. We've gone over the circuit design, the switching frequency, the fans. I haven't heard them come on yet, apart from during health check. Let's see whether the fans come on when the signal increases a bit. So I'm gonna go up to sort of 12 volts. I'm gonna allow 40 amps in now. Let's just see whether the fans come on when the signal increases. No. So I would say the fans are doing heat. The fans are probably heat controlled. So on some of the Taramps amplifiers, like I think the Smart 5, the fans were coming on and off with the audio signal. I think that was, if I check my, it might be maybe it's the Paris that does that. One of the amplifier reviews I've done, the fans come on and off with the signal. Seems like with this Smart 8, this Big Boss 8, the fans are probably temperature controlled, because even with quite a high signal there, we had no fan operation yet at all. So that's cool. Okay, what else do I want to check? Is there anything else you guys like me to take a quick look at in here? Let's read some live chat. Let's see what you're doing. This sparkling water is disgusting. Who would drink sparkling water? I just found it in the fridge. I think we got it from a hotel. Yeah. Bad ground has the ground terminal melted. Oh no, really? Yeah, fair play. Half-bridge amps guys say Taramps don't play lows. I know, it's a misconception. One of my mates is running two MK8s at 0.5. Yeah, nice. That'd be good. I like the Smart 3 and 5. Big Boss line, I like the newer version HD3K also. Delta, hey, just stopped by, bought a whole set of power supply FETs for my amp, hoping this will be the issue. Hopefully you bought them from a reputable supplier like Mouser, DigiKey, Farnell, RS Components. I hope you didn't buy them from eBay or Amazon or AliExpress, because if you did, it's not going to work. Could bad banks cause weird output? Very noisy, no sine wave. Generally no. No, power supply MOSFETs being bad would cause there to be no operation at all, just blowing fuses and smoke from the amplifier. So your power supply FETs probably aren't the issue, so I wouldn't waste your time replacing those. You need to go through the amplifier with your oscilloscope and identify whether there's any Class D switching, whether all the auxiliary supply rails are present, whether the preamplifier is up and running, whether the signal's making its way through the preamp. Rather than just kind of like blindly replacing parts and just hoping you hit gold. Yeah, by the sounds of it, if the amplifier is actually powering up, then the power supply FETs are not the problem. Can you load it down enough to see if the SMP switching speeds up? That MOSFET current feedback is more than a limiter. See if it speeds up. I don't think I can. So, I mean, I do have some high current power supplies in the workshop, but they're not hooked up by any means at the moment. I can do 40 amps from my bench power supply. I mean, that's not really gonna get the amplifier loaded by any stretch of the imagination, is it? So my amplifier should be arriving with you tomorrow or Saturday. Cool, thanks, man. I don't think the SMP would speed up. So if the power supply switching frequency was to speed up, it would need different transformers. It would need like different supporting circuitry. I'm almost sure of it. So I don't think that the speed of that's going to change at all. And if the speed of this was going to change, then it would have to be done at the microcontroller, because the microcontroller is generating the pulses for these. So yeah, I can't see that being a thing. Also, the Snubber network would be different on the drain of the FETs, would need different values. I can't see that would be a thing. I've never ever once seen any car amplifier where the power supply switching frequency changes under load. That would be very strange. Why the hell are you drinking that? It's just a drink I found in the fridge. I thought it was still water. I just brought a drink up from the fridge to have while I was doing my live stream, and I thought it was still water, but it's sparkling, and I didn't realise it was sparkling. But I'm streaming now, so I'm not going to go back to the fridge again. Let's see if we can get the sparkling out of it. There's not much left in there, to be fair. SineWave02 wants me to remove the smart circuitry. I mean, that could be done. You could turn this into a dumb 8,000 watt 2 ohm amplifier. Yeah, you could do that, no problem at all. Oh, it's still disgusting even when it's flat. Blech. When I power on my Smart 5K and power it off, you can hear a pop through the speakers. Yeah, these amplifiers don't have a relay to isolate the speaker terminals, so you might get a little pulse through the sub as the output section winds down, because the output inductor, you have to think of it a bit like a mechanical device. An inductor is a bit like a flywheel. It's got mass. So if you think about something really heavy, alright, let's just grab something circular and random. Alright, that's heavy. It doesn't matter if it's heavy. Alright, here we go. Can I reach it without my camera coming unplugged? There we go. Right. So imagine, okay, so this is a flywheel, it's heavy. So it's got a lot of mass. So if you were to turn it like this, it's very easy to turn something very heavy slowly because you overcome the inertia because you're spinning it slowly. However, if you wanted to oscillate this heavy wheel backwards and forwards very quickly, it's going to be very hard to do that because the inertia of it is so high that you'd have to like be really strong to get it to do this really fast. Would be really hard. Now I can do this because it's very light, but if this was really heavy, I wouldn't be able to do that very quickly. So now imagine that this is this is basically a mechanical low pass filter. So it's allowing DC, which is just continuous rotation. So this is DC, so it's allowing DC through because obviously you're not changing the direction, so the inertia is overcome and it has stored potential energy. You can do low frequency oscillations through this mechanical inductor, but if I try and oscillate it really quickly, I can't because the inertia is too high. So high frequencies from my hand don't make it through the drive shaft connected to this flywheel because its inertia is too high. So I can't make the drive shaft oscillate backwards and forwards really quickly because the inertia is too high. Well, I can make the drive shaft oscillate backwards and forwards really slowly because I can overcome the inertia because the speed is lower. So basically when the amplifier starts up, okay, the output inductor here is filtering the high speed switching coming from the FETs and it's allowing the sine wave through. But when you first turn the amplifier on, the first pulse of from the MOSFETs is going to jerk this a little bit. The first pulse on this side is going to jerk a little bit, so you will get a little bit. You'll be able to feel it if you are grabbing the drive shaft of this flywheel here, and the high frequency oscillation started. You'd probably be able to feel like a little jerk in the drive shaft as that started up. So that's why you maybe hear a pop sometimes through the speakers when Class D oscillation begins. And a lot of amplifiers have a relay so you don't hear that, but it's not a problem. Got them from Mouser. Okay, cool. So you bought genuine parts, but I don't think your issue is related to the power supply FETs. So I will probably not bother replacing them first. Try and identify what the actual issue is before blindly replacing parts. The FETs did need to be replaced as I found some shorted. Oh, okay, so you did actually find some shorted. So this is like mid-repair. So you've repaired bits of it. And you still have an issue now rather than this being the only issue. Okay. And two had mismatched batches. Well, yeah. Okay, in that case, definitely, yeah. Replace all the power supply FETs for the same batch, brand new, known good FETs, and then identify what the issue is with the noisy output, because that's unlikely to be power supply related. Did you ever do anything that audible current limiting on the power supply? I remember you making a vid on it, ideas. Did you ever do anything about that audible current limiting on the power supply? Oh, on my bench power supply? No, I haven't even looked into that at all yet. But yeah, it would be something cool that I'd like to look into doing. My bench power supply has a kind of output header on the front. There's probably a signal on there that goes high or low when the constant current lights up. So I could connect that to some kind of buzzer. That would be cool. Do you check out the dual channel curve tracer yet? I haven't, no. I haven't checked that out yet. Alan says, can't find your PM or email. I have a Alto Professional Mix Pack Express. The voltage on the fan is only 8.15. Wondered if you could have an idea for anything we want to look at. So basically, guys, if you want to message me, facebook.com/bearvids. You can message me on there. Variable switching frequency is smart. It increases efficiency for low load conditions. May be weird, but the fact they have current feedback could be variable. I don't think it is. Like, I would literally put money on the fact that it's not. I suspect that you would need other changes, other things going on in the power supply to deal with the fact the frequency was changing. I don't think you could just use the same transformer setup and the same snubber setup for a variety of frequencies. That wouldn't make any sense. I suspect some more complicated circuits and some more complicated SMPs do that, but I don't think that they've done that here. Can you test the difference between Sound Digital 100k high voltage old version versus new version? I don't think I can, unfortunately, because firstly I don't have one of those, so unless Sound Digital send one of those to me, I'm not going to get one because I'm not going to buy one. So if Sound Digital want to send one of those to me, fine, but I don't also have a 300 volt power supply in the workshop, so I'd have to kind of cobble something together to test it. I could look at the circuit and determine what the differences are, but it's not really something I'm interested in doing. I don't want to promote those amplifiers to end users. They are freaking dangerous for random bass heads to be trying to connect up in their vehicle. I do not want people connecting high voltage amplifiers to 300 volt battery supplies. No, I'm not even going to ever do any videos on them because I don't want people to, you know, learn more about them. I think they're a terrible idea to be selling to end users with no training or experience. Callum, yeah, dude, stop stressing, man. Don't worry about it. If your amplifier gets here, it'll get here, and your tracking will say that it's here. So don't worry about it. Just if your tracking says that it's here, then it's here. If your tracking says that it's not been delivered yet, then it's not been delivered yet. So just chill. Don't worry about it. Just chill. I would like to send you both amplifiers to understand why people like the older one. There's enough people using these to like have an opinion on them. I honestly really don't want to do any videos on those. Sorry, buddy. Also, I doubt you're in the UK. If you wanted to send me these amps from overseas, you're probably looking at like $400 round trip at least, just on shipping. So, but if you want to take some pictures of the board, some good close-up pictures of the board and all the components, and send them to facebook.com/bearvids, then I'll just take a look at the pictures for you. See you later, Jamie. Thanks for jumping on. You want me to finish the audio pipe 3K? Okay, fine. I'll do a stream on the audio pipe 3K probably next week. I'll get it off the shelf and dust it off, and we can finish the mods on the stream, and I'll like then cobble together a video for part 3 and put it in the van, and yeah, go from there. But yeah, guys, is there anything else you guys want me to look at on the Big Boss 8? Should we plug in a sub and just see how it plays? I mean, it's going to play fine, it's going to play normal, but you're not going to see anything about how it plays just by looking on it on the stream. Is there anything else you want me to look at on the circuit? I'm just kind of trying to think about what else I want to look at about the circuit to like make for my video on it. What I should probably do is watch back my review of the Smart 5 and just remind myself of how I did that video, because that was a really good video, if I do say so myself. Oh, what rectifiers? Yeah, I didn't even look at the rectifiers, did I? Let's have a look at what rectifiers is using. He's probably just using some variation of 1620 or 1640. Are you going to do some PA amplifier repairs? I have been dabbling in some mains powered stuff recently, yeah, I do need to. The problem I have is that a lot of the PA amplifiers I'm working on have switch mode power supplies, and they have faults with the switch mode power supply circuit, and it's because of my setup is tailored to car audio repairs. I need a way to actually probe and scope all the way through the SMP running on the mains, firstly safely, and secondly where I can actually follow the waveforms. Obviously with mains powered SMP, you can't just hook the scope up to like a ground reference, because it's not quite like that. It's not as simple as that. So you're going to need like a differential probe or like a isolation transformer for the scope or something like that. I need to be able to follow the AC through the board, see it get rectified, see it sitting ready on any MOSFETs, and probe any driver VCCs. I need like, yeah, I need a way to just do that safely. I might actually have a handheld scope coming. It's only 2 megahertz though. It's like a handheld multimeter slash scope all in one thing. Some company wants to send it to me to test, I don't know. So I will be getting one of those. I don't know if that'll be fast enough. Should be fast enough, but yeah, PA amplifier switch mode power supply repairs are a fair bit more work, but I do need to learn them because I am getting more switch mode power supply main stuff in, and they're very different to car amplifier switch mode power supplies. So I do want to learn them a bit better, and I want to kind of come up with fun ways to safely work on them without the high voltage being present. Because with a switch mode power supply, obviously you're going to have the high voltage supply. That's the kind of thing that it's going to be switching. But then all of the control circuitry, all of the PWM generation circuitry and the switching circuitry, etc., that runs on low voltage. That runs on like anywhere from 5 volts to 20 volts. So I want to kind of get my head around and get used to injecting and how to inject those lower voltages for the control circuitry, so that I can diagnose a switch mode power supply fault with the switching circuitry without actually having the mains rail voltage rail present. That's one thing that I want to do a stream on probably next week. So yeah, the rectifiers that this is using, they're just 1620s. Yeah, good old MUR 1620, and it has the common anode and common cathode, so the CT and the CTR. Nothing different really about that. Make an isolation transformer from a pair of identical microwave transformers. Oh, okay, so you would obviously just run the mains into the primary, and then the high voltage secondary, you'd run that into the secondary of the other one, and then just take the 240 out of the primary of the other one. That's a very low effort way to do it, I guess. That's not a bad idea, other than like having like 2000 volts like somewhere. You don't really ever want 2000 volts somewhere. Ideally you'd want to take the secondary off and wind another same identical 1-to-1 ratio primary, but this is the Big Boss 8. What do you think of sound digital amplifiers? Not a fan. In general, like some of the amplifiers they've made are fine, or they're okay. Some of them are absolutely terrible. So in general, I'm not a fan of what they make. They charge a ridiculous amount of money for some really bad design choices, especially in their smaller amps. Like their little 4-channel full range Class Ds, absolutely horrendous assembly design choices. Like, and loads of like floor noise. Like Taramps have made some really affordable Class D full ranges that have like barely any floor noise and sound great. No turn on pop, decent circuit design, decent assembly quality. Sound Digital comes in, charging like 5 times as much, and you turn the thing on, it's like, and then all the solder just snaps within like the first week because of its stupid design choices. No, not a fan. Oh, here Nicholas says, no, actually, you make a single transformer with a pair of primary windings by cutting them open. It's super easy to do. I will see if there's a YouTube video on that, because yes, if I can do something like that, that would be freaking awesome. I wind a new secondary. I made a stick welder once with 2 MOTs secondaries. Aren't Sound Digital the same as Taramps? No, their circuit designs are actually very, very different. I know they might look the same to the untrained eye, like they have transformers, caps and inductor in the same sort of place and whatever, but no, the circuit designs are actually a fair bit different in Sound Digital versus Taramps. So basically, the way that I've been working on switch mode power supplies at the moment, you guys are going to laugh at this. I made do with what I had. So the way that I've been safely working on switch mode power supplies while also having mains isolation at the moment, let me just get the Big Boss 8 off the bench and I'll show you. Oh man, what do you think it is? How do you think I've done it? I bet you it's not how you think I've done it. But I do need a better solution, but this is how I've done it for now. So that reminded me, so yes, the way that I'm doing it is I'm taking advantage. Switch mode power supplies generally will operate from 110 volts to 240 volts. They'll accept any of those voltages and they'll just adjust the circuitry for that. So what I'm doing is I'm actually using one of my, I'm just going to hold the camera, one of my Inova Pro PA amplifiers. So this does 2000 watts, I think it is, 2000 watts at 8 ohm bridged, if I remember rightly. I could be wrong, but I think it does like a fair bit of power at 8 ohms bridged. So basically, I'm just hooking this up to the mains, okay, feeding it with a 50 Hz sine wave for my signal generator, and then I'm running a 16 ohm resistor in series with the bridged output terminals in series with whatever mains device I'm like trying to repair on the bench. So yes, and I just calibrate my signal generator so I can turn the signal level from like basically 0 up to 110 volts worth of output on the amplifier, which obviously I can then ramp up slowly, a bit like a variac. So I've kind of almost got like a switch mode variac in that sense, I guess. I don't know. But the amplifier is protected by the 16 ohm load in series with the device that I'm working on. So if the device presents a short circuit to its mains, then there's a 16 ohm load in series with the amplifier, which the amplifier is perfectly happy driving a 16 ohm load because it's rated for 8 ohm anyway, so that's not a problem. Yeah, it provides isolation from the mains. I can actually deground my scope, and I can connect my scope ground to one of the amplifier's bridge outputs as a ground reference, so that I can then use my scope to actually probe around the power supply if I wanted to. And yeah, that's kind of how I've been getting around that at the moment, but I do need a proper solution for sure. Yeah, and I also want to be able to, like I said, power up switch mode power supply. Let me just show you. Here we go. So this is a switch mode power supply that I was looking at earlier today, and I didn't do much diagnosis on it. I just had a quick look at it, see if I could find anything wrong with it. So this is a switch mode power supply out of an amplifier. Okay, so you've got mains coming in here, all right. You got live and neutral, and the earth just connects to there. Okay, this then the AC coming from the mains gets rectified by this, by the looks of it. Okay, and that then seems to sit on this MOSFET here, which is an IRF P460. So it sits on an IRFP 460 and it gets buffered by this capacitor. This is a 450 volt cap, and basically at times there is, even when you only have, so this circuit's doing a bit more than that, because even when I only fed this at this switch mode power supply with 110 volts, I actually ended up with about 390 volts in the cap. So there's some kind of boosting or something going on, whereby when you feed this with 110 volts, you end up with about 400 volts DC in the cap. That then sits on the IRFP 460, which is here. And the IRFP 460 then seems to get some switching pulses on its drain, that's basically on that sort of 400 volts on the cap. But it then doesn't go any further. The output, this is supposed to create bipolar rail voltages for an amplifier. You can see here, this terminal, you've got these capacitors, which are supposed to have the rail voltage in them. I'm not getting any rail voltage at all. There's nothing. So there's something wrong, obviously, with the circuit somewhere. It's not producing, it's not working as a switch mode power supply. We're getting no output voltage on the output side. But we are getting 400 volts on this capacitor. And we are getting some kind of switching going on the 460. We've got a power factor correction IC here. This IC is what is generating the pulses for the MOSFETs. There's another pair of IRFP 460s over here. So we've got two IRFP 460s over this side, one over this side. This little one is a diode. That is a NF004GU something 60, 1660. So that's a 1660. So that's a little diode sitting right there. You've then got a bunch of inductors, which are all very, very loose. But I have checked, they are all actually connected to the board. But yes, very loose inductors here. Gee, is that one connected? That one's heckin' loose. Let's get this out of the way. Yeah, no, that is connected. Let's just check the continuity across that inductor. Yep, so that is connected to the board. It's just very, very flappy around. I guess I didn't need to worry about vibration damage or anything, because this isn't like a car amp that's going to be on a mounted to a box or anything like that. So you've got an inductor there, and then you've got obviously a big transformer-y boy here. This driver, this thing which is generating the pulses for the PWM, seems to have its gate PWM output going through this little inductor here before it goes to the gate of these. But these MOSFETs, these IRFP 460s, basically have continuity between gate and source. Well, it's like a sort of 10 ohm resistance, but I don't think that it's got a, what is that, 5.7. So you've got 5.7 ohms between gate and source of this this MOSFET here. And do you have it also on this one? Yeah, you also have it on this one. Yeah, 5.7. I think that's just reading the winds of the transformer, because as you can see, the gate and source here goes to the transformer by the looks of it. So yeah, I haven't really looked too much into this, but it's not creating any output rail voltage. This little daughter board is basically another switch mode power supply that creates plus minus 15 volts, plus 5, does standby and fan and stuff like that as well. This board is working. I am getting plus minus 15 volts and stuff like that on this board, but yeah, I'm not getting any rail voltage on this one. And I haven't tried it connected actually to the rest of the amplifier board, which I might need to, because there might be something like, it could just be something as simple as the standby signals not being connected. I haven't done too much digging with it yet, but I do want a way for me to be able to sort of probe all of these small signals and stuff around here without 400 volts sitting in this bloody capacitor. That would be nice. So I need to kind of scratch my head a bit and learn a bit of switch mode power supply repair and diagnosis safely on the bench, in the same way that I do with amplifiers, powering up with low voltage rail and stuff like that. That would be nice. And I also would love to learn a bit about how these work, because I'm looking at this and I'm kind of got a decent-ish idea of what it's doing. It's obviously switching, it's rectifying the mains coming in, it's boosting it if need be to a high voltage like 400 volts, and then obviously it's switching the high voltage through a transformer, which is then getting rectified again to give you bipolar rails. Like, you know, I get the basis behind it, but I want to really know how it does that. Can you rate your top 5 Brazilian amps? Powerus, number 1. Taramps, number 2. Possibly Causus, number 3. But the only reason the Causus is number 3 is because I've never seen one. I know that it's the same company as Powerus. Causus and Powerus are the same company, but I don't know like what the differences are. So I can't put it as number 2 because I've never seen one, but I will put it as number 3 because given it's the same company as Powerus, I imagine they're pretty great. So probably Powerus, Taramps, Causus, then probably, depending on the model, this is where it gets difficult, because I like the Stetson smaller amplifiers, like the little 3K, 4K little ones, they're great. I don't like the Stetson big ones. Stetson would be last on the list if it was like big amps. The Sound Digital I would probably put 4th if we're talking about the big ones. See, it's between Sound Digital and Banda. Yeah, I'd probably put Sound Digital 4th, then Banda, but very close. Banda and Sound Digital kind of trade blows in my mind, at least. And then Stetson last. But if we're talking about small amplifiers, I'd probably put Stetson 4th, then I'd put Banda, then Sound Digital last. I don't like Sound Digital small amplifiers. Why do my solder tips get worn out so fast? One tip just doesn't last as long. Am I buying cheap ones? I'm not sure. I've only ever bought soldering tips that have the heating element built into them, because that's how mine works. So I've never bought like regular soldering tips. These things tend to last me about a year, maybe more. 10 tips in a month? Jesus, maybe an iron's too hot. I don't know. What happens to them? Do they snap, or do they just stop like taking solder? Maybe you need to clean them? What do people have to say about my mains voltage solution? Let's see. Amp BB8s need repair or not? No. No, the Big Boss 8 is just an amplifier for me to look over, because I'm making a video on the Big Boss 8. So I wanted to use this live stream so you guys could see my first impressions, and for me to make notes for a video script that I'm going to make on the Big Boss 8 to tell everyone about, you know, how good it is or how not good it is or whatever. So yeah, there's nothing wrong with the Big Boss 8. It's functionally fine. I just wanted to have a look at it because I've never seen one, and I thought you guys might like to see my thoughts on it. 40 kilogram isolation transformer, yeah. See, I don't need anything that passes much power. Whatever isolation transformer I use just need to pass like, I don't know, 100 watts if that. Do you have an MD8K there that you can measure the 15 volt regulator voltage at 12 volts? I don't, unfortunately, buddy, but it should be 15 volts. If it's not, you've got a problem. Oh, wow, that's crazy. Recoil beefed up a 3K sound digital design, beefed it up better parts. It's called the Recoil DII 33. Did they really though, or is it just a Chinese clone that they said that they beefed up? Let's have a look. Any other pictures of it, or is that the only one? Oh, there's a video. Okay.
Where'd you guys? Devices for the power.
What? Wait, this isn't right, is it? That's not the right amp. No, that's not the right amp. That is a generic Chinese circuit design, like a audio bank or something like that. Yeah, I can't find any guts pics of it. If you got one, then send it to me. That's so jank, I love it. So good you'll probably never change it. It does work, like it's a solution. It works for now. That's an active PFC. Oh, the single IRFP 460 is power factor corrector. Okay. So then the two other 460s over this side are probably the ones doing the switch mode power supply stuff. Actually, these are diodes. These two big boys are diodes, and then these two. No, hang on a minute. What am I doing? Right, sorry. This one here is. Right, these two are. Yeah, sorry. These two are 460s, IRFP 460s. Those ones are connected to the kind of little IC there that's doing the switching, but there's no pulses going to those. And then over here you've got a couple of big chunky diodes, but yeah, I wasn't getting any pulses by the looks of it to the gates of these. Have a look at learning electrical repair. He's got some good vids on switch mode stuff. Thanks, Cirrus. I will check it out. Use a worksite transformer. That's the cheapest way. The only problem with that is it doesn't limit current. With the amplifier setup that I've got here, the 50 Hz amplifier setup, I can limit current quite easily on that one. Input to the voltage reg should be about 22 volts. Yeah. Yo, what's up, Luke? Did you ever end up putting the Smart 5 base in the van for some testing? I think I did. It was okay. The problem is that the van has some monstrous impedance rise, so I think I wasn't really making the most of the Smart 5. Like in the van, because of the DDZ4s, I need like stupid amounts of rated power to clamp like some power. So, for example, I was running a Taramps HD 10K at 0.5 for like 2 years, and I was barely clamping like 5K, and that a Taramps HD 10K at 0.5 is trying to make 20K. That's basically 20,000 watts of rated power on paper, and I was clamping like 5 kJs of rise, so not the best amplifier for the van. if you had to buy at 2024 an amp for a 13W7, what would it be? What would it be? What would I buy? That's a tricky question. If I had to buy a brand new, I would probably buy. Yeah, I mean it's probably going to be PowerOS PW2500 or a Smart 3 base. I know that one of the SQ guys, quite reputable SQ guys, is currently running a 10 amp Smart 3 base that I modified for him. I just modified the, I got rid of the high pass filter because he's running an infinite baffle setup. It sounds great, yeah, sounds amazing. So there's nothing really about bass amplifiers that sounds super different from one amp to another. It's just preamp crossover settings, and then the rest of it is your box and driver. The amp isn't really a thing that changes how it sounds. So I would just go for something modern, efficient and cheap, because there's no point spending $800 for 1K when you can spend like $150 for 1K. Like, it's the same. As long as the amplifier is decent circuit design and it's built well, you don't need to spend $800 on 1K. Oh, H1 Nicholas, I love it when he gives me some advice because usually it's very usable. Look at the auxiliary supply coming from the main transformer. Usually there is a small cap that dries out, 22 to 47 microfarads. Okay, so I have basically no idea how this even works, but you're saying that the transformer might have some auxiliary wines for like low voltages. And if a cap dries out, that would prevent auxiliary voltage getting to... But then how would it start up in the first place? That's what I'm a bit confused about. So basically, the way that this SMP seems to be working is you've got a couple of IRFP 460s over here. This chip here is generating gate drive for them. It looks like it's generating gate drive for them. And I did actually get the model of that earlier. If I can bring it up on Google, we can see what that is. We can see where the VCC comes from. What was it? It was freaking... I don't know. Alright, it is a... almost impossible to bloody see. 3843B? 3843B, yeah. So this appears to be what's driving the gates of the 460s. Designed for offline and DC to DC converter applications, so the pinout is right at the bottom of this datasheet, I think. Here we go. So pin 1, compensation. Pin 2, voltage feedback. Inverting input of the error amplifier is normally connected to the switching power supply output through a resistor divider, so we can check that. 3 is current sense. A voltage proportional to inductor current is connected to this input. PWM uses this information to determine the output switch condition. Then we've got timing resistor and capacitor, ground, output, which is going to drive the gate. It's going to drive the gate. And then VCC is pin 7. This pin is a positive supply of the control IC. So let's just start the basics and see where VCC comes from. Is the reference output provides charging current for capacitor. Okay, so let's first of all look at pin 7 of that and just see what that's connected to. So where's pin 1 of this? Pin 1 seems to be on this side, so pin 8 would be here. So pin 7 would be here. Okay, there's a little capacitor here, which is probably buffering, you know, the VCC supply. So I probably got that right in terms of that pin. So we need to find out what else has continuity there. Maybe there's a resistor that's acting as a current limiter. Josh, recoil DII 3300.1 guts video. Are you saying that there's a guts video on YouTube for it? The IC gets its power usually through a high value resistor from the rectified mains to start it up. Okay, once it starts switching, the transformer gets its power supply from the auxiliary supply. Okay. So I'm not finding continuity to any resistor from that pin. So I wonder, have I got that pin correct? Is that actually pin 7? So yeah, that would be that way up. So yeah, that is pin 7. You can see the trace there. And it goes to... the only places that pin 7 goes is to this capacitor and this transistor, and that looks like it. Unless it has a trace going off this way, but I haven't found anything yet. So this is a 2X transistor. We've got a 2X and a 2T, and they have the pin 1s connected to each other and pins 2 connected to each other. So this looks like a standard kind of NPN and PNP driver. But that would make sense actually, that it has VCC. Like if 2X is the NPN driver, then that would obviously need VCC the same way as this chip needs VCC on that pin 2 there. And then that should be ground, which is pin 5. I imagine. Did I get that right based on the data sheet? Let's have a look. Pin 5, ground. Yeah. So that's basically a MOSFET driver right there. Just like these transistors are your MOSFET drivers. So that means that there must be something else that supplies pin 7 with VCC somewhere. There must be a trace that goes somewhere else. I suspect it goes. This way, under the chip. This way. Let's see if we can find it. Maybe I should remove the chip and just see where the trace goes. I can't see a via. That capacitor, the other side is ground, so it's not anything that comes through the capacitor. Not that it would be, because obviously it's DC block, but yeah, not finding any other continuity to pin 7 other than to this 2X. There must be a high value resistor rectified from DC. It must be. It could be the transistor. It could be using the transistor as a crude transistor regulator. No, it's not. The transistors definitely. These are MOSFET drivers. Because these are connected to the output. I think. Yeah, these are connected to the output. So the output that drives the MOSFET is pin 6. So pin 6 drives the MOSFETs. 1, 2, 3, 4, 5, 6. So pin 6 connects through this resistor to this pin here, pin 1. So these are definitely the MOSFET drivers. Got yeah. So there must be something else that has VCC. I'm going to go to the top of the board and see whether there's anything on the top of the board that I can see that has continuity. Oh, there we go. There's a little capacitor here, so it definitely does go up. That trace does go up to the top of the board somewhere, because we have continuity on the top of the board to this little film capacitor here. C15. Okay, so let's check what else has continuity on C15, because we are making our way to the top of the board through a via somewhere. So there is a trace that goes to the top. So yeah, it's right there. So we should find something else, or a trace that leads somewhere else. Looks like it goes underneath the transformer possibly. There's no components under the transformer, which is good. Aha! There we go. I've just found continuity to the header for this PCB right here. Goes down through there. So maybe the VCC is supplied on this board. Possibly. Pin 4. It's either being supplied by this board, or this board is needing it as well. I'd be willing to say this board is needing it rather than supplying it, because this board has its low voltage outputs plus minus 15 all over this side. We don't have any continuity to any of those, so it's not like this board is generating some VCC that then the main board is using. I suspect the pin 4 here is an input from the main board to this board to use. Maybe do a high resistance test from the bulk cap to that chip's VCC. That's a great idea. Let's do that. Let's just get my multimeter cam connected again, because it's gone all glitchy as it always does. Snake cam. There we go. So let's turn the multimeter to 2 mega ohms, and let's test the resistance between the VCC for that chip and the bulk capacitor, which is this bad boy right here. Okay, it is completely open. So, well, 2 meg, it's completely open. Let's go up to 20 meg. 20 meg, completely open. Nothing at all. Multimeter is working because I've got 1.2 meg across my fingers. So, yeah, if this is using that circuit design whereby a high value resistor is between bulk and the VCC, then that resistor has gone open, but I don't know whether that is actually how this works. I should try and probably just power it up and try and measure a voltage there to ground. I guess I should just do that. But either way, I think we will leave this for another stream because it's got pretty late here in the UK. So guys, I hope you enjoyed that little overview of the Taramps Big Boss 8. I will be making a video on that. I've made some notes during this live stream on what I found. So I'll be making a video on that, probably be releasing back in the next week, something like that. Once I've had time to film it and edit it, do the script and everything like that. What's your thoughts on the product? I haven't seen the base face DSP, but I would generally not really buy anything base face. It won't have been designed by base face, so what you'll be buying is you'll be buying a factory generic DSP. If you want to buy a DSP, don't skimp, buy a Helix. That's really, really nice DSPs. But yeah, we'll look at this SMP on another. So what do you use as dummy load? I just have some big ass resistors I bought from eBay. They're like 1 kilowatt continuous 4 ohm resistors. USB scope isolated is $100. Cool. I don't want to use a USB scope. I don't want to have to use the computer for anything testing related. I want individual, like, dedicated units for doing their own thing. Do you have a ESR meter? Yes, I do. I do have a tester for that. But yeah, guys, hope you enjoyed. I will catch you next week probably for a stream. I might be tempted to do a little one tomorrow, but I might not. I'll probably catch you next week now for a bigger stream. We'll either be looking at this SMP repair, or we'll be looking at maybe another mains powered PA amplifier repair. I've also got an integrated amplifier repair to do. I've got a few mains stuff recently to repair, so we might be doing that. So yeah, guys, take it easy. Hope you had a good time. Have a great weekend if I don't see you before then. And if you've got any questions, message me on Facebook, Facebook/Bearvids, facebook.com/Bearvids. And yeah, I'll catch you in the next one. Peace out.